Hello everyone, welcome back. Let's talk about the last item of the 4 items that we were talking about. We were talking about 4 articles, and all 4 articles are brought into one big article at the end of every one of the videos that we have. Every one of the 4 videos that we have regarding sort of this interrelationship that exists between the 4 articles. Well, make a long story short, we already talked about a look at some probability theory. That was the first article that we talked about. We talked about Wallace's formula for pi. And we talked about Stirling's formula, a very important approximation. It becomes very, very close to an equation the bigger the number n is. Okay? So we talked about those, and at the end, we are going to talk about the normal distribution. So basically, guys, the way it all plays out, I guess you could say, put these in some kind of order, I guess. The 4 articles pertain to 4 videos. At the end of each one of the 4 videos, you'll have all 4 of these articles scrolling in order. The 4 videos, and consequently the 4 articles, are the following. As we said, the written articles, all 4 of them will be at the back of each one of the videos. The video just talks about a particular topic, but I'll have all 4 articles scrolling at the end of each one of the videos pertaining to this. The videos are a look at some probability theory, Wallace's formula for pi, Stirling's formula, and what we're doing now, the normal distribution. Those are the videos. And also, there are the 4 articles, and they'll be at the tail end. All 4 articles will be at the end of every single video, including this video right here. So I'll probably go back and forth, probably cut a few times, and then fill up the board and talk. It might be a little more time efficient. It's hard to know what the best way is to do this. I seem to think that that's maybe a real time efficient way to do it, given the topic. But let's just see what happens. Well, as we said, it's the normal distribution. It's written about as loudly as I write anything, I guess. The normal distribution, the last of the 4 related articles, or at least somewhat related articles that we've talked about, and of the 4 related videos that we've talked about a number of times already by now. This is it. The last one of them, for those 4 related articles and videos, is the normal distribution. We obtain the normal approximation and the normal distribution function and other conclusions for when n, the number of trials, small. Now remember, we were doing other stuff when we worked with other mathematics, when we were talking about Wallace's formula and Stirling's formula and perhaps other places. Look, when we talk about probability theory, they were using capital N instead of small n that I'm using right here. Again, I mentioned be aware of that. Well, here we go. I really meant it. Be aware of that. What's going on here is they're talking about when small n, so I'll just say it's pretty obvious it's small n, so I'll just call it n. N and NP are both large. P is the probability of success for each trial. It's the same probability for every single trial. The same probability of success, called P, exists for our purposes right now. We're looking at the binomial distribution. P is the probability of success for each trial. Q is the probability of failure for each trial. It's either going to succeed or fail. We're not going to get too philosophical about this. It's either success or failure. Well, the probability of success plus the probability of failure are complementary to each other. It's either one or the other. P plus Q is going to be equal to 1. R equals number of successes in n independent trials. So R is the number of successes. Earlier in that discussion pertaining to probability theory, we were using small n, I think, for the number of successes and capital N for the number of trials. Now it's small n is really the number of trials and R is the number of successes in n independent trials. N is the number of independent trials. N minus R, well, if there are R successes, it's either success or failure. If there's n trials total and R of them are successful, the rest are failures. So n minus R equals the number of failures in n independent trials. Then they go into this a little bit, and I'm going to do it as well when I come back. I mean, we'll terminate this a little bit and then go a little further when we talk. I like to try to write a lot of this stuff in the middle of the board, you guys, but it's kind of the same phenomenon. Either you succeed or you fail. In n trials, you're going to have R successes and n minus R failures. That's it. It's either a success or a failure. R plus n minus R is equal to the total of n trials. If this many successes, the rest are failures. R plus n minus R, yeah, it does end up to n total, adds up to n total trials. This B sub R, think of it as B for binomial, pertains to the binomial distribution, and the P and the Q, as we've talked about in the past, P pertains to probability of one success for one trial. Q pertains to the probability of one failure for one trial. And I want an array of R successes and n minus R failures, a total of n trials. R of those n trials are going to be successes. The complement of that, for maybe lack of a better word right now, if there's n total trials. If R of those n total trials are successful, n minus R are failures. So success R times and n minus R is failure. So success is going to be R times that it's going to occur. Failure is going to be n minus R times that occur. Together they add up to n. Well, this whole thing, and I'm going to write this again when I leave for a little bit. We're going to write this right back on here. We're going to start right with this guy and talk about it a little bit. I'd like to have that right in the middle of the board, to be honest with you, when I do it. So we're looking at something like that. Let me kind of debate with myself a little bit here when to cut out of this, and then I'll just come right back. I'm going to do that a couple times on this video, guys. Probably cut out with you guys a little bit and say it. I think it's probably a good idea. Let me. Yeah, sure, a whole lot here. So you'll see exactly how we want to do it, guys. There's going to be a lot more written here. Something here. And some things I'm going to skip over, guys. I'm going to have you just read through it when we're doing it as well. But we'll see exactly where we want to go with this, how exactly we want to play this. It's a little bit of it's some pretty deep water we're going to get into. But I'll see how, like I said, we already have gone into the deep water in the notes, so I might refer pretty heavily to the notes. But I think there's still a good amount of stuff that I need to put on here, guys. All right, so we know that. Let's come back. When I do come back, guys, we've got this right here. So let me stay a little bit. Let me just stay before I cut out of this thing. And then we'll just come right back to this stuff, you guys. The thing I got, the B of R function pertaining to the binomial distribution. And we've seen the binomial distribution. We've worked with the binomial distribution. It's been mentioned a number of times in one way or another. It's been referenced a number of times in various circumstances. So we know what that's about, and we have reference to it. Let's take this guy, let's write him in the middle of the board more or less, and then kind of talk about a few things, or at least write it in a place where it's even a little bit more clear to look at. So trying to get some approximation here, we'll talk Okay. Okay, we'll have it on here. I'll say a few things and we'll kind of go with that. For this, related to the binomial distribution, some sort of binomial function. And again, we've been here. There's not going to be something. It's just some other stuff that happens that we got to kind of be careful about. We're not going to lose a tremendous amount of sleep on it. But again, it's just I think it's important for us to at least take a relatively strong look at this normal distribution and how it derives and stuff like that. Okay. Well, yeah, we've said this. Now we've said this. We've said it at other times. We can do it. So you're looking at this right here, and they're telling us that r factorial, n factorial, and the quantity n minus r factorial are quantities that we will replace by their Stirling approximations, and then put each of these approximations back. We're going to replace. Remember, the Stirling approximation is very, very close to being an equation the bigger that n becomes. Now, I've written that in some, perhaps somewhat awkward manner when I talked about the Stirling approximation, but it is still an approximation, guys. But in the limit, it is a great approximation. And the bigger the n's are under consideration, it is an outstanding approximation, and it gets even better as n gets bigger. So we're going to take factorials. We're going to say that, well, for that to happen, the factorials have to be big. N factorial has to be a big number. R factorial has to be a big number. The quantity n minus r factorial has to be a big number for us to be able to use the Stirling approximation to get to where we're going to go. Let me try to say a lot of things. There's a lot of jumping around, I guess. There's a number of ways you can write the Stirling approximation. There's a number of ways to write the Stirling approximation, you guys. Here's one of the ways. I think I just mentioned it, but I didn't write it down the last time, how it could be written like that. But this is, again, an approximation. It is an excellent approximation when n is big. And if that's not enough for you, make n even bigger. So we're going to use that for n factorial. Well, how are you going to do that for r factorial? Well, in place of an n factorial, you're going to have an r factorial here, and you're going to plug things in appropriately. In place of the quantity n minus r factorial, in place of n factorial here, you're going to put the quantity n minus r factorial here. In place of n factorial, you're going to have r factorial, et cetera, et cetera. And we're going to see how this thing plays out. So that is Stirling's approximation. We're being at the big thing here is, as we said, the thing way up top there, b of r equals n factorial over r factorial times the quantity n minus r factorial times p to the r times q to the n minus r. That's associated with the binomial distribution. This expression is associated with the binomial expansion, which expresses the probability. It expresses the probability for r successes in n independent trials. What does that mean? Well, the r successes can occur in any order as long as they occur within the n trials that took place. They could all occur the first n trials. The first r trials of the n total trials, they could all occur right there, or the last r trials of the total of n trials that could occur there, or any arrangement within those n trials. Well, this expresses that reality for r successes. This takes everything into account using combinatorics to give you that. Now remember, we talked about the coefficients and stuff like that, the binomial coefficients. Well, that's kind of where this is coming from, and that means here you could have a particular expression. You could have p to the 20th times q to the 30th. Well, 20 and 30 is 50. It's an order 50 It's a degree 50 because 20 plus 30 is 50, but all that's in there, yeah, that can occur a bunch of ways, but I don't care about the order of it. I just care about the combinations, not the permutations, the combinations. And this tells you how many times those combine. This tells you how many are in that p to the 20, q to the 30. Okay, that's kind of where they're coming from. So pretty phenomenal stuff in that regard, you guys. This, again, we've got to emphasize this, guys, when we say this. That expression, I just underlined here, is the expression associated with the binomial expansion, which expresses the probability for R successes in n independent trials. We are asked to suppose that R, n, and the quantity n minus R are large enough to permit the use of Stirling's formula. Hence, I wrote Stirling's formula down there. We're observing it. We will make all the appropriate substitutions and manipulations within this, and we'll play the game at that point. You know, and when we do that, that association, that what we write is going to be at least an approximate equality. So let us proceed when we do it. Okay, we gotta be extremely careful when doing some of this stuff, guys. So let me take this reality, which becomes a very, very close to being an equation. The bigger that n is, the bigger the factorial. The bigger the number whose factorial we're finding, the closer to an equality that Stirling's formula will become. Okay, we talked about that when we talked about Stirling's formula. So we're right here. Let's plug in all appropriate values to that, and it's going to become B of R, and again, approximately equal to, and here we go. First of all, let me, I guess, write the easy thing to write down, I guess, and hopefully I got enough room to do it. We got P to the R, Q to the n minus R. Okay, that was pretty easy. This guy's kind of out of the loop, so to speak. It's not going to be part of something that we're going to consider for Stirling's approximation anyway, so write it down. But we are going to consider n factorial. Yeah, well, n factorial is roughly equal to n to the n times e to the negative n times the square root of the quantity 2 pi n. In the past, I had that square root of n here. I put it right here, and it was n to the n plus a half. And I mentioned something about it. You'll see it in the actual written notes. You can go in this direction as well. All right, let's go in that direction right now. Well, okay, that top thing's pretty easy. I'm not having to manipulate too much. N to the n, e to the negative n, and square root of 2 pi n. I don't know how I do it, guys. I write huge. I got a huge board, and I still end up running out of room. But anyway, there it is. This guy's kind of, let's not put him on there. Let's put him right here. Maybe that helps a little. I hope you can see that okay, guys. Then what? Well, the rest is, it gets a little on the messy side, guys. But we're going to, like I said, we'll jump around as we need to jump around, I guess. R factorial, how are you going to write it? I'm going to write it the same way I'm writing this. I'm just going to put the R in place of n, the R in place of n, the R right here in place of n, the R in place of n, the R in place of n. Okay. Yeah, okay, I can buy that. And then the other one, let's just actually do that. So here's the R. Again, I think the notes, guys, are going to be a lot easier to kind of follow than the more or less live film presentation that I'm doing here. The notes, you can kind of go at your own pace. Okay, guys, did we just write that right down? Yeah, we did. Sure. It looks a lot like this guy. It looks a lot like this guy with the N, but here you're just going to put it with the R. Yeah, okay. Sounds good to me. How's the other one going to play out? We got a little sort of watch out with the other one. With the other one, it's going to be n minus r. Well, yeah, that's like the new n in a sense. To the n minus r, right? It's behaving like n to the n. here's your new n, here's your new n. It's n minus r to the n minus r. And the other one is e to the negative n. Well, this is your new n, as we said, right? Doing this. And square root of we better have faith in Stirling's formula. In the right circumstances, we said it's going to work out. We're saying that n's huge. N's a really big number. R's a really big number. N minus r, they're all big numbers. You know, when n is really huge, you know, reasonably speaking, R can be really huge. You know, NR and N minus R are all relatively large for you to be able to get something like this. So then they look at it, guys, and they say at the end of the day, not really quite the end of the day on that thing, but they're saying, is there approximately equal to, that does not, I don't know what this looks more like a train wreck, but that means approximately equal to, guys. I don't know, is there anything to see here? Yeah, there's a whole lot to see. I'll see where we can go here with this. Yeah, it's some pretty interesting stuff if you really want to be careful about it. This is, that's e to the negative r. That's e to the quantity negative n minus r. If you multiply these two exponentiated quantities, you're adding the exponents. And when you add the exponents, you end up getting e to the negative n. At the end of the day, when you multiply these two, e to the negative r times e to the negative, the quantity n minus r, this is e to the negative r. The minus here is negative n. Minus and minus is plus. So it's e to the negative n plus r plus negative r. It's e to the negative n. Well, wait a minute. If it's that way, if it's e to the negative n total when you multiply the two, these guys together is e to the negative n. That cancels out. That cancels out. There's a lot here. There is a square root of 2 pi right here, and there's a square root of 2 pi right there. And, you know, they go. You got the square root of n left here, square root of r left there, and you got a square root of the product, 2 pi times the quantity n minus r. So, it looks the way it looks, I guess you could say. Try to give this guy maybe a little better look here, guys. This guy's not really being affected by what's going on here. You just got to figure out what's going on. You're trying to. This guy's not affected. Yeah, it wasn't affected over here either. You're trying to get an approximation to this using exponential functions or using something without having the factorials in there. Guys, if you're slick, the factorials are all gone. You got exponentiated quantities here, and what they're going to play out to is its own pretty fascinating matter in its own right. You got n to the n, you got r to the r, you got the quantity n minus r to the n minus r. I don't know what to say on that. And I got this stuff right here. So I'll tell you what, we see some stuff. We're going to kick it around a little bit and see what we can say. Well, they're claiming there's a p to the r right here. Yeah, he was unaffected. There's a q to the n minus r, so they're kind of putting this in a different place for us. Again, I got to make this clear, you guys. I'm sorry, I should have done this at the very beginning. It is in the written documentation, that's for sure. Once again, what I have been doing and what I'm going to do, the following, or what preceded this, was heavily influenced by brilliant scholars such as Courant and John, and Sokolnikov and Redheffer. What I'm doing here with the normal distribution, the following is drawn very heavily from the brilliant work of Sokolnikov and Redheffer, from their work Mathematics of Physics and Modern Engineering. We've already mentioned that. Once again, all four of these documents, if I hadn't found Sokolnikov and Redheffer and Courant and John and other people related to the probability theory we're working for, we have them documented, wow, this would have been incredibly difficult to do. Who knows when I would have gotten it done or if I could have gotten it done. So the tremendous work that they've done. That obviously has to be said, and that's documented as well, okay? So all the best to them with the work that they're doing, guys. So what we're looking at there's a couple, and I'll tell you a couple other things here, guys. In a bit, I guess we'll just take this as we need to take this. I'm just trying to figure out how I want to write this, actually. All right, so we got this. Let me just kind of follow. Let's figure this out. We got, for lack of any other way to look at this, let's look at some sort of symmetry or some sort of identity of numbers occurring in different places, and maybe, for lack of a better way to say this, maybe that makes it easier to look at. Look, here, make a long story short, you guys. Here's P to the R, here's R to the R. Here's the quantity n minus R to the n minus R, and here's Q to the quantity, to the power of the quantity n minus R. So I got n minus R as an exponent, I got n minus R as an exponent, I have R as an exponent, and I've got R as an exponent, so maybe there's a connection here. Maybe there's something we need to talk about. At least maybe this is easier to visualize if we do this. Make a long story short, look at what you did over there, look at what got canceled, look at what remained, and then try to deal with it. You've got this, and you've got this. And we already just kind of said that. We're looking good. We got that. Wish I had a little more room, guys. I mean, it's a little different than how I did it in the notes, but I did what I did. All right. Just multiplied when you're doing this. They're getting multiplied, guys. Okay. And you got n to the n. Well, that one doesn't really link up easily with something. Yeah, and you got the square root of n somewhere. Yeah, you had it here. I mean, you wouldn't know by the way I wrote it, guys, but there was an n right here. It was clearly there, and then I just started drawing arrows and bunching things up, and it easily could get lost. So there's a square root of n, and there's a square root of r. Well, I guess there's some sort of symmetry in the look after you pull something like this. You know, it looks something like that, you guys. So let me write that a little bit better, actually. But that's what it is. That's what it's looking like. All right, it's looking like this. We said it was going to look, and again, the more I look at it, the less I like the way it looks. So let me just write it again, guys, and then we'll end up erasing this. But this is the thing right here. There it is, looking like that, and then that's just going to be equal to all these guys, this product right here. And let's write that a little bit better, actually. So what we got here same thing we wrote. Let's just hopefully it's a little more legible, for lack of a better way to say it. Yeah, it's a lot here. There's a lot of intuition to it, but you got to have it in front of you. It's a hard thing you're going to memorize just right off the bat. I guess you can if you look at it enough times, but you're looking at this. And that's really the big thing that I wanted to kind of talk about. You got to here, and we're just going to say, and look, we're essentially saying, when we're going to get into the normal distribution, there's either success or failure, and the number of successes is R, and R can range from a whole lot of successes or no successes, and they're saying, okay, within particular limits, you guys, this normal approximation is going to be excellent. And the bigger the number n under consideration, it should all work out fine. The binomial distribution, in a sense, is almost the heart and soul of what we're going to be using to move toward, finding the normal distribution function. It's just the binomial distribution is going to resemble, for large number of trials n, for very large number of trials n, the binomial distribution is going to look very, very much like this thing called the normal distribution. And that's basically the argument here. They say a lot of stuff. There's a lot of subtleties here. For our purposes, we're not worried about that. The numbers are all very big, especially n. And even if R is very big, but n is so much bigger, that's on the other end. You can go to the extremes of the normal distribution too, if R is big enough. If it's a huge number of trials, guys, even the zero, if there's 1 trillion trials and there's 1,000 successes, man, that's close to failure. Totally, I guess you could say. So the numbers are big enough, you can make it work out, and even there, the resemblance of the binomial distribution when n is a very big number to the resemblance of the binomial distribution when n is a very big number to the normal distribution is quite striking. And they show that in textbooks oftentimes when you're looking at it. So you've got something like this. From here, you got something looking like this, you guys. Let me just try to see the language that they're trying to speak on this stuff, you guys. Then what they do here, this is kind of the key. And we're going to just see it's the key, and there's a lot you got to do to get this thing under control. To try to, you're getting, you use Stirling's approximation. We know a lot of we use Stirling's approximation just now. We're going to use what we know about the binomial distribution and the mean of the binomial distribution, which is n times p, the variance of the binomial distribution, which is n times p times q, and also the standard deviation of the binomial distribution, which is simply the square root of the variance, which is the square root of the product n times p times q. So that's going to come into play as well. Also, Taylor's formula is going to come into here. So a lot of stuff that we've already discussed is all going to come into play to get this thing under control. I am just trying to think of how I want to say this, how they're saying, okay, I see what they did. Okay, so what they're doing is they take n factorial, they take the square root of n rather, and they put it right here. And they take this guy, n to the n, and they kind of like just, so basically you're going to take this and put it right on top of here. A square root over a square root is the square root of the entire ratio, and then n to the n is what that is. The r, let's see where the r is. They did something. Some sort of, I think they're doing, they do something else that's very much of great interest. I just, you got this, you got the nth root of this. Now, I'm sorry, the r, the root of r, this somehow gets approximated. Just want to make sure I can see everywhere that it could be. Oh yeah, the r just comes right underneath. So what we're going to do is you're going to take this r and put it in here underneath the radical, because it's underneath here is a radical. The product of radicals is the radical of the product, so it's going to go right here. The square root of n is going to be right on top of here. The square root of something over the square root of something is the square root of the entire ratio. So at the end of all this, you guys, it's going to look not a whole lot different. It is the same thing now, where I'm about to write. The end of all that, it becomes n to the n right there, and the square root of this entire thing, and that's where the r came, and the r was right. Right. 2 pi r yeah, correct. We get to here. Yeah, true story. That'll work. It's the same as what we had earlier. You got to tinker with it a little bit, but the square root of n and the square root of r both just came over, got underneath one radical, each one got underneath a radical, and the ratio of radicals is the radical of the ratio. So we did this, we got to here. Then they say, is there more that you can say? Yeah, there is. I mean, what you can do is, this is pretty fascinating stuff how they pull it off. They take this guy right here, and they said, why don't you break it up? Take n to the n and make it, keep in mind, take n to the n and write that as n to the p times n, forgive me, no, that's not true. They're saying take n to the n and make that n to the r. Let me just see here. Yeah, let's do that. Let's make the n to the r and n to the n minus r. Is that true? Sure, when I multiply exponentiated quantities with a common base, I add the exponents. You add these two exponents, you got n. Yeah, it looks good to me. You're going to put this guy, n to the r, you're going to put him right here, next to this guy. You're going to take this guy, n to the quantity n minus r, and you're going to put them right next to this guy. Once you've done that, this guy's out of there. So, let's do it. Q to the n minus r. Let's see what we got. N minus r, q to the n minus r, and I think that'll kind of help us. And this is n to the r. Okay. Yeah, absolutely that's true. Yeah, it's definitely true. And in fact, look at it carefully, ladies and gentlemen. Let's take these r's, these exponents. The product of exponents is the exponentiation of the product. The product of exponents is the exponentiation of the product. The product of exponents is the exponentiation of the product. Absolutely true. Absolutely true. And that all stemmed from this. We played the games with this, and we got what we got. Okay, that's really interesting because, well, look at it. I think we're kind of, it's staring at us pretty well. I think if you really want to talk about it. Let me kind of think here. The way to kind of write this, they can write in a whole bunch of ways, actually. You could take, they do some other stuff here. Okay, well, look, guys, there's exponents that are the same all over the place. Here and here. And a product with, this ratio of the ratio of exponents is the exponentiation of the ratio. The ratio of exponents is the exponentiation of the ratio. Make a long story short, just kind of makes sense out of this. Right, okay. I don't want to go too far, guys, and say something I'm not supposed to say. Okay, everything looks good. NQ, all this. NQ over n minus r, like this. There's different ways you can write that, actually. I'm not going to. There's n minus r right there. And it's all this. Yeah, nothing's changed here. Everything's the same as what we had earlier, you guys. We're not going to sit here. We're not going to sit here and deal with it. I mean, beyond what we need to deal with. I mean, this is okay. We've done this. It's all this. It's all looking good. Yes. Let me, for some reason, I'm just looking at this. Yeah, right. Okay. There's nothing. I think I'm reading too much into this sometimes. And like I said, I copied down from great people, Sokolnikov and Redheffer. And in one instance, I thought I was correcting them, but I'm confident I probably didn't. My correction's probably not right when I did something. We'll talk about it. Luckily, I think if I did something that maybe shouldn't have been done in one particular part of the problem, I guess that was one place where that would be the best place to do it because the result was trivial. It gets thrown out anyway, so kind of fortuitous in that regard. We'll talk about that in a bit. So we got to here. This is nothing fortuitous, nothing anything. This is the way it is. So what? I mean, so what are you going to say about it? Well, there's a number of ways to do it. The above is at least an approximate equality. It's going to be pretty close. They do some stuff here that I don't know how you're going to feel about it, but let's just do it. The argument that takes place, they're saying, okay, let's manipulate this a little bit. And how are they going to say manipulate it? Well, they're saying there's absolutely no nice way to do this, so let me just do it. Let's multiply by the reciprocal of this radical on each side of the equation or approximate equation and see what we can say and what the reciprocal of it. So what we end up getting is b of r times the reciprocal. You multiply by the reciprocal of this radical on each side of the equation, and you get 2 pi r n minus r over n, the square root of that. And that's going to be approximately equal to, and again, I hate this, guys. It just seems like there's not enough room sometimes. That's NP, NP right here, R right here to the R. The other one's N, so this is going to be, and this one right here is going to be N minus R, NQ, N minus R on the bottom. I'm going to rewrite this anyway, so it's going to be okay. But so there you go. There you go. See how we can tinker with this a little bit and play some games with it. All right, this thing right here, you guys, is as it is. I tell you what I want you to do. Right, we got it like this. So here's, let me write it again, guys. I'm never confident how, this is probably quite visible. I think I write loud enough that it's going to be fine, but I'm never entirely very comfortable with it. And then I'll write something and then end up erasing a little bit more. We'll figure out what we're going to do. But we talked, and 2 pi r and that's, we said it's going to be approximately equal to, I'm just rewriting it so I think you're going to see it a little better over here, guys. And then as soon as you see it better, I'm going to manipulate it some more. Correct. True. Can I ask you a question? If you take the reciprocal of this ratio, if you flip this ratio upside down and exponentiate to a negative r, it's the same as what you originally had. If you take this ratio right here and flip it upside down and then exponentiate it to the negative, I'm just going to make let's put it this way. We know enough. We know that, for example, a over b to the n is the same as, well, it's the same as a lot of stuff. I mean, let's just kind of, But I'm not sure where to draw the line on some of this stuff, you guys, so let me not draw too big a line just yet. Does everybody agree that positive n is the same as negative I mean, I don't want to get into too positive, negative, whatever business we want to talk about. For our purposes right now, let's look at n, and n is some real number. N is some real number. Some integer makes it even easier, but any real number, it'll definitely work. Is it true that negative 1 times negative n is the same as positive n? If you are, is that the same as a over b, put the negative 1 right there, and put the negative n right here? Is this to the negative 1 the same as b over a to the negative n? It is. What's the moral to the story here? Well, the moral to the story is we just did it. I mean, ab to the n is the same as b over a to the negative n. True. Yeah, I mean, you can kind of look at it and say, well, b over a to the negative n, is b over a the same as a over b to the negative 1? If you exponentiate an exponentiated quantity, you multiply the exponents. Negative n times negative 1, negative n times negative 1, negative n times negative 1 is positive n. The quantity a over b to the n is indeed equal to the quantity b over a to the negative n. So the quantity a over b to the n is the same as the quantity b over a to the negative n. And we just showed that way over there to the far right, and we showed it here too. You started right here. We're making this claim. We're making that claim. Okay, pretend that claim is correct. Here it is. Why don't you test it? You test it, you test it, you test it. You're back to here. So the moral to the story is you can take, and they do it. I mean, they've got their reasons, and we're gonna trust them. I mean, Sokolnikov and Redheffer know a tremendous amount, so we're gonna trust their motivation for what they're doing. What they did is they took the NP over R, and made it R over NP. They took the NQ over N minus R, and made it N minus R over NQ. Yeah, but if they're doing that, that's negative R. That's the negative. Okay, well, we already kind of went through, we went through that song and dance in a more basic form to play all this to get where we're getting. So, I mean, we saw a lot. Yeah, sure did. Let's start erasing a lot, I guess. Luckily, we got it all on film, and we have it all in the notes too, guys. So if we got to gloss over something a little bit, we can be a little more rigorous about it when we get to the actual notes. Okay, so let's take a look at that. It's a lot there. I mean, they look real similar, and then before you know it, it's looking a lot different, but it's coming from that one idea of the binomial distribution. The binomial distribution in very, very many ways, when n is a very, very big number, the binomial distribution is going to resemble quite a bit. It's going to resemble quite a bit the normal distribution, but we're going to give it a look where we don't have to deal with all factorials. Well, what got us out of the woods with those factorials that aren't easy to deal with? We made the factorials look like something that was in terms of exponentiation, n to the n, e to the negative n, et cetera, using Stirling's formula. Wallace's formula for pi is going to come into this too, because there's going to be factorial notation, and we can get out of the woods with that if we can make it look like pi, and we can. And we said the factorial stuff in other regards resembles n to the n times the square root of 2 pi, or n to the n plus 1 times the square root of 2 pi times e to the negative n with Stirling's approximation. So you're getting out of the woods and not dealing with the very awkward nature sometimes of factorial notation, of factorial mathematics involving factorials. It's a little more convenient if you have it in terms of exponents. Well, okay. I mean, that's kind of the argument that's going on here. That's kind of premised. That's really what we were trying to do with a lot of this stuff, you guys, when we were doing it. So it's looking something like this. Again, step by step, you're taking this to where you want to go, and see if there's some kind of grand shortcut or some kind of real easy, relatively easy equation that's describing a lot of the reality that we're encountering here. Well, this is true. We're looking at it. Okay, we manipulated. You kind of wonder why do that. I mean, you already had the n over p. You already had the n times p over r. You already had the n times q over the quantity n minus r. They got their reasons. We got it. They did it. They got their reasons. Sure, and there it is. So we got all this. It's looking like that, you guys. The above is at least an approximate equality. Let us proceed. So this right here, you guys, is an approximate equality. Likely gets better and better the bigger that n becomes. Stirling's formula sure got better and better as n got larger. As n got larger, Stirling's formula became a much better formula. It's a great formula from the get-go if the numbers are big, and the bigger the numbers get, the better the approximation is, and it's very useful to use in a lot of mathematics. We're using it right now, in fact. We've already done it. We got to here. This is at least an approximate equality. So you got to proceed. They go about it and it gets a little, like I said, some of this stuff can get a little messy. Let me tinker with it as much as I can. I don't have Sokolnikov's book right with me right now, but I seem to remember I drew a different conclusion than he drew. And if it's going to be a judgment between him and me, opt for what he did. Okay, obviously. I mean, but I was pretty close in what I said. Perhaps there was, perhaps there's other things going on that I didn't see. Anyway, it turns out what I did to sort of correct matters probably didn't correct anything. I'll talk to you about it soon, but luckily it doesn't matter. The approximation is such that whatever the right conclusion is on some part of this problem, that particular part of the problem gets thrown out because it goes towards zero, so it's not going to enter into the calculation. So it's fortunate in that regard. So let me see if I can kind of go around this a little bit. Okay, we got what we have right here, you guys. They are saying, let's play a game here. Let capital A equal the square root of 2 pi r n minus r. That looks awfully familiar. Yeah, it's what's underneath. It's the one thing that was right in front of the br. I guess it's just a lot easier if you can give it a shorthand. What's the shorthand? What do you say you call it A? Lowercase delta is going to be equal to r minus np. R is number of successes. NP is the mean. NP is the mean of the binomial distribution. We called it capital NP when we talked about a look at some probability theory. When we looked at some of the brilliant work that was done by by Turner and some other person as well. So, yeah, it's fine. This is mu. This is the mu. This is the mean value. This is the mean value of successes. The average number of successes for n trials. And this R is the actual number of successes for n trials. There's actually R successes. There's actually R successes in n trials. What does that mean? Well, I don't know. There's n trials, man. You could have 0 successes out of n. You could have 1 success out of n. We're not going to worry about that. You know, what we said earlier, how big these things were, big numbers to deal with, that's fine. But let's put R anywhere. Let's have R run the gamut from 0 to n. You could have, R could be 0. No successes out of n trials. 1,000,000 trials, only zero successes. 1,000,000 trials, only 1 success. 1,000,000 trials, only 2 successes. R is equal to 0. R equals 1, R equals 2, whatever. NP, however, is that 1,000,000 times the probability of 1 success. The probability of 1 success times the number of attempts times the number of trials. N number of trials times the ratio of successes. N number of trials times the ratio of successes will tell you N number of trials times the probability of the success per every trial. Every one trial has a probability P of success. In n trials, n times P is the average number of successes that you're going to have if you do a total of n trials. That's what we were doing earlier in a look at some probability theory. And this is the actual number of successes. And things aren't always perfect, are they? You're not going to, oh, gee, every time I'm getting the average. No, you might get everything successful in n trials. Every single one of them is a success. Very unlikely. None of them are a success. Also very unlikely. Somewhere in the middle, yeah, it sounds about right, but it doesn't mean you're going to get, but whatever, you can get anything. This runs the gamut. R can be from 0 to n. All right, and they play some games here, and so let's play the games with them, I guess you could say. R is the number of successes straight out. That's delta plus NP. And they write it like this. R equals, they like to write the NP right here. They don't jump into this and call it mu. Later on they kind of do. Or not really. I don't think they do, actually, to be honest with you. It's there. We know enough, so we're going to keep going there. Okay. R equals NP plus delta. Sure. Yeah, isn't P, based on our previous work, the same as N times the quantity 1 minus Q? 1 minus Q is P. So yeah, I think that's right. And R equals N minus NQ. Here we go. Yeah, okay, kind of so what? Well, I'll tell you what. Why don't you subtract R on each side? Subtract R on each side and add a positive NQ plus a negative delta on each side. All right, Yeah, okay, you're kind of, I guess we're all kind of wondering here. Well, wonder no more. There it is. You got this, and, this could be useful. This could be useful. A lot of this stuff could be useful. I mean, we're looking at this. We also got, I didn't really emphasize it hugely in the notes, but hey, what the heck, we got to here. You got all of this plays a role. This guy right here looking like this, he ain't looking too bad either. Yeah, I mean, I think there's enough symmetry here. I wanted to emphasize this. I didn't really quite emphasize this as much in the notes initially, but okay, you've heard a lot of the speech I'm trying to deliver here, guys. Let's go. We said this. Okay. Put an A right here. R is NP plus delta. N minus R is NQ minus delta. There's an NQ on the bottom here. This is rather interesting. There's a lot here. Let's talk. I mean, let's talk a little bit here. We can say for this right here and this right here, let's talk. Let's talk a bit. We could say that this guy right here, the square root of this rather convoluted situation, the square root of all of this, the square root of all of this is just going to be, well, it's the same thing, right? The square root of all of that, which is this right here, is just A. So that's, okay, not bad. Okay. Still equal to this. I don't know. People can draw this very well. I'm certainly not one of those people that draws it very well. Got any ideas here? Yeah, I got a couple. I mean, we can do a lot. R is this, NP plus delta. N minus R is NQ minus delta. So there's some kind of symmetry here, for lack of a better way to say it. Yeah, that's true. We know if you distribute the NP into NP, you get 1. And the NP into delta, you get delta over NP. So you got NP divided by NP is 1 plus delta over NP. NQ over NQ is 1. Into here is minus delta over NQ. So, yeah, I agree with that too. Maybe that's why they did it. They flipped it upside down so somehow you get something on top that involves some kind of an addition. As we look at it, there it is. I mean, we're looking right at it, guys. So as we look at it, it is going to just try to, yeah, I don't think there's much of a thing here. Let me, so there it is. So we're going to say NP into here is 1, NP into here is delta over NP. NQ into here is 1, NQ into this one is negative delta over NQ, and the whole thing. Okay, let me write that down and let me keep manipulating a little bit and see if that's of interest. Okay, so we got what it's looking like, guys. B of R times A, and we did all that division that we talked about, all the games we're playing here, guys. So let me please kind of be careful here when I'm doing this. 1 plus delta. Stuff's not difficult, but it's easy to make a careless mistake with it as well. And that sort of puts us in a bad spot in the derivation. Now, the derivation's already there. We can always hook around, guys. You do have it in the literature. So maybe that makes it a little easier to look at. Yeah, it does. I got more to tell you, though. Didn't we say that, we're saying it again, didn't we say that R was equal to the quantity NP plus delta? Didn't we say that the quantity N minus R is equal to NQ minus delta? Why don't you kind of like run the gamut on this thing, man, and just say, well, we're looking at it, 1 minus, okay, so let me kind of give myself a lot of room here, guys, if you don't mind. Negative R, you know, they had the negative R and all that other business. Well, the R is the quantity NP plus delta. And, okay, we got all these. We know what they are, guys. We've already done them, so let me start getting rid of stuff. There's just you always want to keep as much of this up here as possible, but we've got it. You've got it in the written notes. And you got it on the film too. So that's 1 minus delta yeah, it's a bit of a mess. Now let's look at A again. You know, we're going to look at A again, but this is pretty big. I mean, you get to here. Yeah, it's okay. It's not too bad to look at. Again, it's important because somewhere in this process, guys, if we're really slick about it, guys, we lost all the factorials. That's a big thing. Without it, you know, if we're not paying attention, Stirling's formula let us lose all the factorials. You know, if they show up again, I guess we'll get rid of them again. But hopefully we can. But if we've lost a lot of stuff here, and we're not looking at anything too crazy. The exponentiation, you're not dealing with base E. You're not dealing with factorials, at least at this juncture and probably foreseeable future. We'll see how this proceeds. But we got it as it goes. Now we're going to look at A again, you guys. Okay, so let me leave as much of this as I can right now, and eventually we're going to come back to it and probably do some more. I mean, this is quite the lengthy process, you guys. I think when you're reading the notes, you're going to go through it a lot faster than I'm going through it. And I'll give you a heads up on something on the notes, you guys, and we'll see what we can say. All right, so we got this. Let's talk. A equals, okay, we know this. Not much of a manipulation beyond, at this point. Just say this. We know that, and then we say here we go. You remember, I regret, well, I think there's enough there that we know. R was NP plus delta. N minus R was NQ minus delta. N minus R was NQ minus, don't worry about the negative out here. Talk about this. The quantity N minus R is NQ minus delta. The quantity R is NP plus delta. R is NP plus delta. N minus R is NQ minus delta. Okay, let's write that down. That's R. Keep wanting to say mu, you guys. I mean, mu's in here somewhere. I already said that, but what am I doing? Okay, well, so we got NQ here minus delta. There's some kind of symmetry here going on. Yeah, true story. See what else they do. Yeah, they try to pull something on us here. We'll figure it out. They write down NPQ. You already know that NPQ is the variance. That's sigma squared. That's the variance. NPQ is the variance. Here's what. Okay, let's try it again. Here's what it was. Everything here to my left. Everything here to my left is what A is. If you multiply by this on top, you got to multiply by this on the bottom. You got to multiply by the same. If you multiply by the same thing top and bottom, it's still an equation. True. So let me try to think. That's pretty interesting stuff, you guys. Watch this. Watch carefully. You got N times P times Q. Really? That's N times P times N times Q. Indeed. Why don't you have that? Why don't you have this NP go into here? Why don't you have this NQ go into there? And why don't you leave this guy alone? Fascinating stuff, guys. Well, this looks really familiar. Let's deal with it. In fact, I don't know why I made this square root so big, because there's going to be nothing in the denominator from what I'm gathering here. And I'll look too in the notes, guys, to verify this, but let's go right here. NP goes into here once. NP goes into here, delta over NP. What? That looks like this. NQ goes into here once. NQ goes into here, negative delta over NQ. That looks like that. Okay, pretty important stuff. What's going to happen is, let's see what we got. 2p 1 plus delta over NP. Pretty neat. And this is 1 minus delta over NQ. Okay, guys. Let me just make sure. Yeah, it's fine. So a lot of times what they do is, at that point, guys, you got all this. Again, I hate erasing this stuff, but, you know, we're looking at this, we got this. See what we got. Well, you know, just to rearrange the thing a little bit. Put this NPQ is pretty serious business. This NPQ, we know from the past, is the variance. The variance is sigma squared. Yeah, it's underneath the square root symbol. The square root of sigma squared is sigma. It's the standard deviation. The square root of the variance is the standard. There's standard deviations in there. Wow. Surprising. At least at first glance, very surprising. Two pi NPQ. Okay, let's see how they wrote it. Yeah, that's fine. 1 plus delta over NP. I just keep wanting to write mu because NP is mu. Well, cross that bridge too, I guess. Eventually. At least at some level, you're going to cross that bridge. 1 minus delta over NQ. See what they want to say here, guys. See what we want to say. I mean, we write to here, because there are approximations that get made. How intuitive are they? Depends. That's what our background is. Depends why they're making that approximation, what the assumptions are made. So we said these are big numbers. N is big, NP is big. If NP is big, I think NQ would be big too. If N's a big number, a lot of things are big, I guess you could say. You know, a lot of what you're doing. Maybe that's where they're going with the assumption on this. But we got it to here. You got something like this. And then they say to you, ladies and gentlemen, they say to you, this thing right here, this guy right here, They're equal. So, you know, they're trying to get a way out of this thing. Now, we know a bunch of stuff. We wrote a few things here. We know that. I just want to kind of take this potentially in slightly a different way than I was showing it in the notes. Perhaps not. I don't know. We'll see. We'll see what's easier for everybody. Look, they're going to make an assumption here that delta is not really that big, and NP is really big. Delta is really not that big, and NQ is really big. What's tiny divided by huge? Close to 0. That's close. This whole thing is close to 1. What's tiny divided by huge? Close to 0. 1 minus that is, you know, this is going to be something barely bigger than 1. This is going to be barely smaller than 1. Man, you multiply them together, they're just about 1. That's the assumption they're making there. They're making the assumption. Now I'm going to go in a little bit different order than how I wrote this, you guys. But a little bit different order here. Not a big deal. Not a big deal at all. They are. I just want to see. I want to agree with the kind of order I want to take here, guys. Let me, since we're here, we're here. I think it's just easier right now, just given the location of where I am in relation to the data that we've written on the board, the information we've written, the mathematics that we've written on the board. Let's work with what we got and take it from there. Again, we're gonna, you know, it's gonna work. We're gonna work under the assumption that this guy right here is gonna be 1, or, you know, if n is big enough, it's gonna be 1 or close enough to 1. Tiny bit smaller than 1, tiny bit bigger than 1, tiny bit smaller than 1, and tiny bit bigger than 1. When you multiply them, it's 1 for all intents and purposes. And then, so that's just 1. You know, 1 times 1, or at least the product is 1 or very close to it. And you got A is equal to the square root of the product, 2 pi NPQ. They are working under the assumption that, I'm just going to argue this point for a second here with myself. Yeah, we're not going to argue it too much. We don't need to argue it that much, guys. The basic premise is this. They're assuming that the absolute value of delta, and delta was, I want to just kind of come back to it. Delta was R minus NP. Down the road somewhere, let me just kind of, delta is equal to R minus NP, which is mu. Why? And that's why I keep writing it, I guess. But that's what delta is. And there's a lot of ways you could argue this. Sure is. Sure are. NP plus delta. I'm sorry. Right. R equals delta plus NP. Delta equals N minus NP. Delta equals R minus NP. Okay. So they are telling you the mean of the binomial distribution taken away from the number of successes or failures, for the most part, is not a very big number compared to NPQ is really huge. It's a lot bigger. That's the assumption. It's a lot bigger than delta. That's their argument. We're assuming n is, p is a constant, q is a constant. P is a constant, q is a constant. You multiply them together, you get what you get, but n is massive. And it is just generally n is the number of trials, and if it's a huge number of trials, if that's not huge enough for you, we'll make it even larger. We'll make the number of trials much larger. If that's still not enough, we'll make them much larger yet, even more. Bottom line is, this thing is massive compared to what's going to go on here. This thing right here, take away from the two, there's not going to be an incredibly huge, there could be a very big difference between them. Typically, more often than not, there isn't. Whereas this is huge. And that's kind of the argument here. Well, if that's the case, for one of these, if that's the case, we said, I don't know, Q could be, there's some trivial things here. P could be for sure. It is for sure when you flip a coin, it's going to land. What's the probability of it not landing? Well, I don't know, short of I don't know what happens. It's just, for our purposes, it's guaranteed to land. I didn't say it's going to be heads or tails, true. You guys understand, everybody understands that NP times 1 is just NP. That's for sure greater than or equal to and if Q is not allowed to be 0, it could be if Q is equal to 0, or if P was equal to 0, this greater than or equal to thing. If Q is a non-zero number, this is a ratio between 0 and 1. This guy's bigger than that. NQP. And Q's bigger than that. At most, they could be equal. If P equals 1, they're equal. In every other instance, NQ is bigger than that. If P equals 1, then they're equal. If P is not, then Q has some other value. NQ is bigger than NPQ. If Q equals 0, they're equal. Anything else, this guy's always bigger. NP is bigger than NPQ. NQ is bigger than NPQ. Except for some exceptional circumstance that we've already discussed. Are you serious? Yeah. NP is bigger than this. NQ is bigger than this. They're both bigger than this. Both of these, aside from trivial circumstances, or not trivial, I guess trivial maybe is the right word. Aside from obvious circumstances where they'd be equal, other than that, NP is bigger than NPQ. NQ is bigger than NPQ. They're bigger than all that, and this is already way bigger than that. So into here, these guys, this is close to 1, this is close to 1. And because of that, In the right circumstances, if not equal, awfully close to it. I can't emphasize how important this is. This is sigma squared. This right here is the variance of the binomial distribution. This is the variance of the binomial distribution. The square root of the variance of the binomial distribution, the variance of the binomial distribution is sigma squared. The square root of sigma squared is sigma. This is the standard, the square root of this is the standard deviation. The square root of 2 pi, wow, we worked with that. We found pi earlier with Wallace's formula. So maybe there's a connection here. But we have what we have. And PQ here, so we're going to see that. Know that I needed to erase that, guys, but there we go. Okay, these are some of the arguments they're doing. They also said, I tell you what, can we do something here? Can we take that thing right there? Okay, we already got this, we got it written down, we know it, we're good. Can we take this right here? And can we get the logarithm of each side of this mess? Well, the logarithm of this is going to be ln br of A see how they wrote it. I want to kind of use they kind of. And then the ln of the other side, the logarithm of a product is the sum of the logarithms. True. The logarithm of this product is the sum of the logarithms. Yeah, we've been there. And I know we approximated, but right now let's not approximate. We were okay. We were justified in doing the approximation because there wasn't anything necessarily too convoluted going on when we dealt with A, and we found that to be the square root of, 2 pi, the square root of the product, 2 pi NPR. There was two factors, and they were pretty straightforward for us. Right there wasn't anything else going on beyond that, or for us to actually get there. So our argument was it was close enough, it was simple enough to look at. The argument is, okay, let's let it go. Let's just make it simple. Let's just remember that we're making the claim that for all practical purposes, A is going to be the square root of the product, 2 pi NPQ. And whatever. Okay, yeah, we did that. Again, the assumption was because delta was much less than NPQ. Yeah, if it's much less than NPQ, it's going to be much less than MP, and it's going to be much less than NQ. We talked about that. Because that's going to be NPQ here, less than or equal to. A lot of times, in very many circumstances, strictly greater than. Okay, so we talked about all that. If that's the way it is, didn't really finish, guys. I kind of left something up there. We want to just bring that out. this thing we did. And let me kind of give my, okay, I wrote what I wrote, but I'm not, well, let me just wrote what I wrote, I guess you could say. NP plus delta and here we go NQ minus delta. Yeah, it's to the negative right there. Okay. When you actually do this, guys, now we said the logarithm, remember we're taking the logarithm of both sides. The logarithm, take the logarithm on each side of this equation, or near equation, or approximate equation, and it'll still remain a near equation. Let's take the logarithm of each side on this equation, or close to it. The logarithm on each side, the logarithm of this is this, and we'll cross that bridge. The logarithm of a product is the sum of the individual logarithms, that's that. Now, the logarithm of something exponentiated, NP plus delta ln 1 plus delta NP. 1 plus delta over NP, rather, I'm sorry. And this right here is negative NQ minus delta true. Now what? Well, it gets messy. It gets somewhat messy. From the Taylor expansion, we said we got to here. We've been playing more than a few games with this thing, I guess you could say. What's going on here, guys? Well, from the Taylor expansion, ln of 1, Taylor's formula, we did that too, didn't we? Yeah, we did it. I probably evaluated it wrong at one point, at least when I did some of the stuff on it. Not then, now, I mean. Then I did it right. I mean, the general form of Taylor's formula, you know what it is. You've seen it. You've seen it in one variable, and then you've seen what we could do with one variable, parameterize it, and actually write it for several variables, for multiple variables, for many variables, for any n variables in n-dimensional Euclidean space. We could do Taylor's formula. And we used the beautiful exponential function as sort of a memory device on how things get assigned and how the derivatives and the factors that are being squared and cubed and whatever are being exponentiated. We use the beautiful exponential function to talk about Taylor's formula in several variables, in many variables. And it worked great. And we talked about Taylor's formula in one variable. Everything was right on that. The problem is once you got this thing, it's a beautiful formula. Make sure you do it correctly, right? And that's kind of what I was saying just now on this. So if you look at this, you've got this. If you play this with Taylor's formula, and that's a long song and dance, guys. It's a long song and dance. It's going to come out to something like this. I got to stop writing mu, even though it is mu, right? Let's see what we got here, guys. So that's NP minus delta squared over 2n squared p squared. I'll talk about this in a little bit. Plus delta cubed. Yeah, it's not the exponential. I'm sorry, it's not Taylor's. It's Taylor's formula. It's just not a nice, easy look at it. I mean, there's a lot of stuff flying all over the place here, guys. I think this is where you're talking about, you know, the delta over NP being equal to some x. And how you want to go there. You know, how you're actually going to do Taylor's formula doing that. You're always starting at, you know, the way it's going to play out. You're always starting at, you got to get, you're using on something like this, you're starting at ln. ln of 1 is 0. So that kind of plays a role. It kind of makes this thing a little simpler at the end of the day when you're doing certain things. But you got to start something like this, and you're probably looking at, if you're going to write it like that, you're looking at something of this nature. And there you go, and so on and so forth, how it's going to be. The way the whole thing plays out is this right here is going to be the f of that, and you're going to set it, you know, how you're actually going to set this thing. You know, you can make it one big X also. The thing is, you can't, at 0, this thing is too much of a, is not going to work for us. At 1, it's going to be 0. There's so many ways you can go, actually, guys, when you're doing this. But just trying to argue how I'd want to do it. If you'd want to kind of look at it, you're looking something of this nature, and then you go for it. I didn't really go into it too much in the actual written notes, so I'm kind of doing this completely cold. We know that f of x is going to be equal to f of a plus I'm sorry, forgive me, f prime at a over 1 factorial well, I mean, I hope it looks familiar because we beat this up pretty good in the past. This is that. We might even want to stop right about here to at least get a feel for what the heck we're doing here. If A equals 1 and x equals 1 plus a, forgive me, if a equals 1 and x equals 1 plus delta, you know, so if a equals 1, you guys, then x is going to equal to 1 plus delta over NP. What the heck does that mean? Well, look at it. Look at it carefully. If A equals 1, f of A, if A equals 1, and f is the logarithmic function, right? F of x is ln x. If A is 1, ln of 1 is 0. You know, so I don't want to erase anything here. So A is 1 and x is 1 plus delta over NP. Well, 1 plus delta, what's 1 plus delta? What's 1 plus delta over NP minus 1? Delta over NP. 1 plus delta over NP minus 1 is delta over NP squared. F A is equal to 1. The natural logarithm of 1 is 0. Looking familiar now? The first derivative of the logarithmic function is 1 over x. 1 over x at A equals 1. 1 over 1 is 1. 1 factorial is 1. So you simply get, my friends, you simply get 0. Okay, you get 0 plus this guy, that was him. And then this guy, that's a 2. The second derivative, the derivative of 1 over x, is negative 1 over x squared. That's negative 1 over 1 squared, which is just 1. Negative 1. Negative 1 divided by 2 factorial is negative a half. Yeah, here's your delta squared. Here's your 2. Here's your 2. Here's your n squared. Here's your p squared. You get it? You come out here. 1 minus, this delta over np, here we go. Yeah, it's to the third. Okay, yeah, third. 2, 2, 2, 1, 1, 1. Okay, to the third. Yeah, it's looking good. Over 3 factorial. Over 3 factorial, which is 3 times 2 times 1. 3 times, underneath now. 3 times 2 times 1 is 6. 6. Yeah, that ain't a 6. Yeah, I know, but you got negative 1 over 2. Negative 1 over x squared. The derivative of negative 1 over x squared, the third derivative of the first derivative of the second derivative, the third derivative, which is the derivative of negative 1 over x squared, that's negative 2 over x to the third. Well, x to the third is 1 to the third. Negative 2 over 6. Negative 2 over 6 is negative 3 on the bottom, which is negative 3 on the... Negative 2 over 6 is negative 1/3. And just make sure that was the case. Okay, no, my mistake, guys. That was negative a half here. This is going to be a positive. Here's why. Forgive me. It was here 1 over x. The derivative of 1 over x is the derivative of x to the negative 1, which is negative 1 over x squared. Negative 1 over x squared, here's your negative 1. That was right. Negative 1 over x squared. The derivative of negative 1 over x squared to get the third derivative is out here. The derivative of negative 1, the derivative of negative 1 over x squared is the derivative of negative 1, the derivative of the quantity negative 1 x to the negative 2, which is positive 2 x to the negative 3. Well, x to the negative 3 is just 1 because 1 is the difference between, because x, no, I'm sorry, x to the negative 3 is, let's have a look here. Right, the A rather. I'm sorry, the A was 1. So x to the negative 3, you ended up getting the derivative. The derivative of, again, we started here, and we got 1 over x, which is x to the negative 1. The derivative of x negative 1 is negative 1 times x to the negative 2. And the derivative, and of course I'm going to run out of room here, and the derivative of negative 1x to the negative 2 is going to be 2x to the negative 3. And our x under consideration is the a, and the a was equal to 1. So if a is equal to 1, because that's the x under consideration, that's just 1. You got a 2 right here. 2 over 3 factorial is 2 over 6. That's 1/3. And x minus a is 1 plus delta over np minus 1. 1 plus delta over np minus 1 is delta over np to the third. Right, that's got to be to the third. 1 plus delta over np, 1 plus delta over np minus 1 is just delta over np taken to the third. That's it. And that's where we're getting this. It's a mess. I'm sorry. It's in the notes, but not quite. I mean, it's kind of extrapolated in a sense. For the notes itself, I mean, the game that gets played here, big time, is a is going to be 1, and x is going to be 1 plus delta over np. And then play the game that you know how to play. Taylor's formula is definitely correct, the way we've done it. You will do the exact same thing. So, I mean, they're basically saying this, guys. You're going to play the same game with the other one. You're going to play the same game with the other one. You're going to say the 1 is going to be the A, and the X is going to be 1 plus a negative delta over NQ. So 1 plus a negative delta over NQ. You got to go plus a negative. 1 minus delta over NQ, 1 minus delta over NQ is 1 plus the opposite of delta over NQ. It's the same argument though. In this case, you know, for the other case, you're doing this. Let me go into this just a little bit, guys, not hugely, but I think a little more so than I did in the notes. And so when you look at this, so on and so forth, done the right way, you guys, and you kind of saw me go with it. I don't think there's a big surprise here. 1 plus a negative delta over NQ. It is just about the same kind of argument, you guys. You're going to get a 0 in the first one, and again, the way it's playing out, it's the same exact argument, you guys, that we had. What's going on? Well, it's the same thing going on for that one, guys. You're kind of working with a being equal to 1. The x, at least this specific x, is going to be 1 plus, which is a little bit more than that, right? Well, it's 1 plus whatever. 1 plus a negative delta over NQ. What does that mean? Well, that means x minus a is going to be 1 plus negative delta over NQ minus 1, which is what? Well, it's negative delta over NQ. That's this one. So what happens when you start doing exponents on? Well, to the n or to the k, for as you're doing it, it's going to be to the k power. That's going to be the k power, because x minus a is negative delta over NQ. And they're playing the game again. This is f of x, because this guy's x. And that's equal to f of a. A is just this guy to my left, on my left side, the 1. ln of 1 is 0. Plus. Well, it's actually whatever, who cares? Then what? What's the derivative? Wait a minute, guys, it's kind of the same argument playing the game all the way through. It is negative, that's 0. The other guy is the first derivative. What's the first derivative of the logarithmic function? It's 1 over x. It's x to the negative 1. It's x to the negative 1. 1 over x or x to the 1 over x, huh? Yeah. 1 over a is 1. 1 over a is 1 over 1. A is equal to 1. That's 1 over 1 factorial. 1 divided by 1 factorial is 1. Yeah, so what? So what? Yeah, this one's this. It's negative delta, NQ. That was x minus a to the 1 power. Well, we said x minus a was this. X minus a was this. Negative delta over NQ. Remember, x is equal to 1 plus negative delta over NQ. And a is equal to 1. When you subtract, you get negative delta over NQ. Yeah, that's what you're doing. What happened with the other one? The other one was the x was 1 plus delta over NP. Yeah, minus a, which is minus 1. That's just delta over NP. That would have been delta over NP right here, and you're taking the power. And that's why you were getting these powers for this one. That's why you were getting these powers for this one. Here you're going to get the same thing. What, to the 1? Yeah, this guy was to the 1. Yeah. Second derivative. We've been there. The first derivative, the first derivative was 1 over x. That's x to the negative 1. The second derivative was negative 1 over x squared. The third derivative, negative 1 over negative 1 times x to the negative 2. The third derivative was positive 2 over x to the third. That's 2x to the negative 3. Put an a right here. Well, a is equal to 1. What's 1 over 1? 1 over 1 is 1. We already got that. What's negative 1 over 1 squared? Negative 1. What's positive 2 over 1 cubed? What's positive 2 over 1 cubed? It's positive 2. So we got 1, we got 1, we got negative 1, we got positive 2. We got 1, we got negative 1, we got positive 2. Do another derivative. You end up getting negative 6, x to the negative 4. Oh, you end up getting a negative 6. x to the negative 4. Wait a minute, this is kind of switching. Positive, negative, and you know what? It's going to keep doing that. Because there's always it's always a negative exponent, and when it comes out, a negative times a negative is positive, and later on, a negative times a positive is negative. Negative times positive is negative. Negative times negative is positive, and it's going to keep alternating like that. Positive, negative, but you got to get it straight. There's going to be numbers here. There's going to be numbers other than 1. 1, negative 1, 2, negative 6, whatever. What happens here? Well, it's a second derivative, isn't it? I mean, second derivative with that guy at 1 there, that's a negative 1. Negative 1 over, that was the second derivative now, right? We got the second derivative. Here was the first derivative. Here was the first derivative. Second derivative, negative 1 over 2 factorial. That's 2. Second derivative, and you're squaring it. Yeah, that's interesting. If you square, that's the thing. This is x minus a. This is the x minus a. If you square a negative number, you get a positive answer. Here, but yeah, the negative already stayed there, though. Here, guys, 3 factorial. Yeah, 3 factorial. 3 factorial on the bottom. And positive 2 right here. 2 over 3 factorial. 3 factorial 6. 2 over 6 is a third. That doesn't change. Yeah, but you're taking the negative. You're taking this guy. The negative. You're taking this guy. Taking this guy right here to negative 3. That's an odd exponentiation. Yeah, let's kind of make the long story short, since it's an odd exponentiation. This thing taken to an odd power is negative. Just tack this on like this and not have a problem with it. Well, this stuff can drive you crazy if you let it. I mean, d cubed over n cubed. It'd be nice if I could write, you guys. N cubed, q cubed. Yeah, that's the x minus a. This is the x minus a taken to the third. That's negative d cubed over n cubed q cubed. Negative d cubed over n cubed q cubed. That negative I'll just throw out here, put it in front. And this thing's going to this one's always going to be negative, it looks like. Let's see here how that's going. Let me look at it. Yeah, every one of them is going to be negative. After the 0, every one of them is turning negative, guys. Let's just see what we got here. D, D, D. Yeah, it's nothing wrong here, guys. Nothing wrong at all. I wrote it slightly differently in the notes. Slightly differently, but it's the same argument. It's the same exact argument. That's fine. There was nothing wrong. There was nothing wrong with the application. There was nothing wrong with the application of Taylor's formula. That's fine. That's the way it works. Well, if you kick this around a little bit, there's something that happens somewhere, and I think there's some kind of debate that can occur, but we're not going to. Yeah, I'm still trying to write. No, I think we're good. I think everything's fine, guys. Everything's fine. It's just so much that's there, I guess. Okay, so the argument's proceeding something like this. When you do this, and this is where I might have made an arithmetic error. No mathematical error should be called trivial, so I'm not going to call it trivial, but if there ever was a case where it's somewhat trivial, well, if it's something that you can ignore because the amount that it is trivial and it won't enter into the final calculation, then okay, you lucked out. You still made a mistake, but you lucked out. That's what I might have done here, guys. So it might be something I have to. This is fine. Everything here is fine. There was something else. I think right about 2 lines down here. I want to just talk about it a little bit, if I could. But again, in the end, this is the argument. The actual argument that I'm giving here as to how Sokolnikov and Redheffer proceed in their brilliant exposition pertaining to the normal distribution. Their brilliant exposition is what I'm following closely. I'm talking more about an arithmetic error that somebody made, and that somebody's probably likely me. But the argument that Sokolnikov and Redheffer are giving is spot on, and we're following it spot on. So that's the main thing to concern yourself with. And then you're going to see what I'm going to throw out, and it doesn't matter in this instance, fortuitously, it doesn't really matter what the exact value is of something beyond a certain point because it approaches zero. It approaches zero in the limit, therefore it's just it doesn't count, and we made sure to not let it count. So that's the most important thing to know. So you got all this, you see what's going on. It is everywhere. These are negatives everywhere. I wanted to double check on that, but you're going to be hitting negatives all over the place. And at some point you truncate this stuff, guys, and that's where it can get kind of interesting. Fortunately, I don't have Sokolnikov's book with me, but you know how to reference it. I told you what the book was, Redheffer and Sokolnikov's book, where we can find this. You can look at that as well. So, okay, guys, it's looking pretty good. These are the arguments. Just have it straight. Have it straight when you're dealing with this. Know who's who, and be extremely cautious because there is a lot going on, and that's just the way it is. I mean, f of x is going to be ln x. X is going to be 1 plus something, in this, whatever. Negative delta over NQ in this case. That's hard enough to look at. I'd like maybe just write it down again. That's what X is. A is 1. So what is X minus A? It's 1 plus a negative delta over NQ minus 1. Yeah, X minus A is just negative delta over NQ. And you play it from there. You're taking derivatives with the logarithmic function. That's easy. The first derivative of ln x is x to the 1. I'm sorry, forgive me. The first derivative of ln x is 1 over x to the 1, which is the same as x to the negative 1. The second derivative, and again, the second derivative of ln x is going to be negative 1 over x squared, or it's going to be negative 1 x to the negative 2. What's the other one going to be? It's going to be, the third derivative is going to be negative 2 times negative 1 times x to the negative 3. Really? Okay, and it's going to alternate back and forth, positive and negative signs. You're going to find the factorial in there again. The factorial there's going to be every time you're doing a derivative, there's some manifestation of the factorial going on, which is kind of interesting. And you're dividing by some manifestation of the factorial. So it should be rather interesting how it all proceeds. We've already taken a shot at it, looked at it a bit. So there you go. You've got all this. You're looking at all this. You've got it in the notes. Let's just get rid of everything, guys. Well, okay. I mean, we wrote what we wrote. We did say ln of b of r times a was negative of the quantity np plus delta. See, np does have a special property to it. That's why they kind of went there. NP is mu, so it's got to have some kind of manifestation there. Then you've got ln of, let me just try to see this. I'm trying to just figure out how I want to say this, how I had it before, guys. Forgive me here. I just want to look at. I'm always a bit concerned about how I approach this stuff. You just don't want to make some big mistake on it. Ln plus delta over NP. So ln of delta. Forgive me. Let's see. Just trying to make it look like I had before, guys. 1 plus delta over NP, correct. 1 plus delta over NP. Okay, that. Plus negative NQ plus delta. I mean, again, there's a lot of stuff, guys, we're doing, obviously. No, hold on here, guys. 1 plus a negative delta over NQ. So like 1 minus delta over NQ. Forgive me. Hold on, guys. Negative NP plus delta, negative NQ minus delta. NQ minus delta, okay. Ln 1 plus a negative delta over NQ, or minus delta over NQ. Let me just make sure that is okay. All right, I probably got more on here, more parentheses on here than is probably necessary, but okay, it's there, guys. And again, we're coming back. I just want to kind of refer right back to where it started. 1 minus delta over NQ. That's 1 minus delta. 1 minus delta over NQ is the same as 1 plus a negative delta over NQ. So yeah, that's fine. I mean, we'll do it like this. Now, we did find out, and that's kind of the way this plays out, I guess you could say. We did find out that all of this is negative NP plus delta, and this mess was the f of x function, and we were kicking it around and doing stuff, and what did we find? We found a 0. We had the 0 in there. Remember, we had the 0 plus the delta NP plus negative It's a lot here. I mean, there's a lot going on, guys. But you got to be careful how the derivative. The one thing that kind of saves you on this thing is the a of the f of a fame in the Taylor's formula for a function of one variable. The a is equal to 1. So all of the ln of 1 is 0. The first derivative of the ln of 1 is 0. The ln of x at x equals 0. The ln of x at x equals 1, a equals 1, is 0. The derivative of ln of x is negative 1 x to the negative 1. The derivative of that, the derivative of ln of x is 1 x to the negative 1. The derivative of the first derivative, which gives us the second derivative, is negative 1 x to the negative 2. The derivative of that is positive 2 x to the negative 3. The derivative of that is negative 6 x to the negative 4. The derivative of that, is positive 24 x to the negative 5. The derivative of that is 24 is negative 120 x to the negative 6. You get what I'm trying to say here? So it's alternating back and forth, and x is equal, the a, f of a, f prime of a, the second derivative of f, f of a, f prime of a, the second derivative of f at a, the third derivative of f at a is 1. So when you're getting the derivative of the logarithmic function, it's relatively easy to keep doing it. There's definitely a pattern to it. And when you plug in x equals 1, in other words, a equals 1, it's relatively easy stuff to do. Now, in this first instance, there's alteration going on when you're getting that derivative. Plus, minus, whatever. Plus and negative is usually the language that you're taking to go there. So you're looking at something like this, you guys. For the other one, you got negative and where's that going to go? Well, it's the same kind of business, guys. We ended up getting 0 on one of them, and then it was negative delta NQ. This stuff's a lot easier done than said. I mean, it's just a lot easier done than said, and it's not easily said, nor is it easily done, but you tend to be able to do it a little bit easier than what it is to try to discuss it. There's a lot going on there, but if you stay mindful of all the steps that are taking place, and there are a lot of them, you should be okay if you stay mindful of what's going on. It's easier done than said in that regard. Whatever. So what happens here is, guys, and I might cut a little more to the chase than I want to at this point, but you're looking at something like this. If you multiply, there's a lot going on here. I mean, the NP cancels NP, cancels one of these NPs, etc. The NQ cancels NQ, cancels one of these NQs, and so there's something going on in that regard. The delta is rather interesting. I mean, so distribute the NP and go all the way across. Distribute the NP and go all the way across. Distribute the delta and go all the way across. Here you got to be careful. I mean, you got here you got to be careful in general, guys. You got to bring the negative in here, and your best bet is bring the negative straight on in, or whatever you do, whatever you get for an answer, multiply by a -1 at the very end. That's fine too. Or bring the negative inside here, bring the negative inside there, and then go for it. Or just take it like this if it's easier to look at. Go for it, then multiply whatever answer you got by -1. Just switch all the signs. Same thing here. Go here, minus delta, that's plus a negative delta. Go that way, multiply by -1. Anyway, there's a lot there. I wrote it in a way I thought I had simplified it, very, very similar to what Dr. Sokolnikov and Red Heifer had done. I thought maybe Dr. Sokolnikov had made a mistake. Whenever you're thinking that somebody as brilliant as Dr. Sokolnikov made a mistake, which is certainly possible, we all make them, maybe in the mathematics, maybe consider that if I'm looking to correct them, I might be making the mistake. But anyway, a little bit, so the numbers are kind of debatable what you can say here. I wrote numbers here that on the far end of what's going on, my numbers aren't really agreeing with Dr. Sokolnikov. It's not really going to matter, and I'm likely the one who's wrong on that. I mean, that's something we could look at and straighten out, actually, if we wanted to do it. For our purposes, we don't need to go there. We don't need to go there. Because after a certain point, some of the stuff, the last equation just seen, or there's going to be other stuff I'm going to write down, is a good approximation, so let's just simplify and proceed. I wish I had Dr. Sokolnikov's book with me. I should have brought that with me right now, but just look at it, make sure I want to make sure I wrote it down right. It's looking good to me right here. This part of it's good. Let me not, let's take a look at this, man. Maybe we got this far, might as well take some good looks at this thing and see what we can possibly say here. Okay, so we're looking at this, just to make sure I'm not doing anything too crazy here, guys. Just want to make sure the numbers are on when we're doing this. NQ minus delta. Right. This is fine. This is all good. This is all very good. NQ minus delta. Let me just make sure, guys. NQ minus delta, yeah. Right. Looks pretty good. Let me take a look at it. If I get the same answer, I don't know, maybe I want to debate it with how people are going to answer. It's not going to matter a whole lot, guys. You're going to see what I'm about to say in a second here. Let me see what I can say. Let's take, well, we're not worried about 0 plus anything. And we're not worried about 0 plus anything. And also we do know that there's a lot going on. Well, we know that too. I'm just going to worry about these two terms multiplied with these two terms. And I'm just going to worry about these two terms multiplied with these two terms. And we're going to take it from there. Let us see here. I don't want to, I'm always apprehensive to erase any of this. Negative of the quantity NP plus delta, negative of the quantity NQ minus delta. I think it looks good, guys. I think we confirmed everything on there. I went into a little more detail with Taylor's formula, albeit not as neatly as I would want to go through it, but I hope you understand the premise of the argument, what you're doing here. The f of A is f of 1. The f prime of A is f prime of 1. The f double prime of A is f double prime of 1. So A is 1, and A is 1, and X is 1, the same one, the A, plus something else, which is negative, which is negative delta over NQ, or positive delta over NP, so there's a lot here, guys. Forgive me for taking so much time on this. I just don't want, it's important enough that you want to go somewhat smoothly on it. Let me just make sure here. Yeah, 1 plus delta over NP, that's your X. And 1 minus delta over NQ, that's also your X for the other scenario. And then A in both circumstances is equal to 1. And that's Taylor's formula. You saw how I did that. N minus 1 minus delta over NQ, 1 plus delta over NP. So they're keeping them here. Why are they keeping them here? Because everything's small. So you got to keep delta over n. You can't just, it can't be made trivial because everything is very small with which you're dealing here, potentially. Whereas with the other one, there was a 1 inside of the whole thing. I mean, how you're doing it. You could say here, what are you talking about? Well, is there a 1 here? Well, yeah, if you divide by NP maybe and stuff, but that's doing something different. Right here as is, you're not playing too many games with this stuff, guys. You're going to keep it as is to start knocking this stuff out. Okay, well, let's do this. Let's kind of settle this thing. Let's see what you want to say about it. So that right there here goes nothing. We're throwing -1 on at the end, guys, right? It's actually -1s everywhere here. There's a -1 right here, and there's a -1 right here. I'll just throw the negatives on at the end if you want. Let's go. NP times this. We'll throw the -1 at the end on all. It's -1 times this, and it's also -1 times that. Why don't you just multiply the whole thing by -1 then? Okay, you do, to each his own on this, just get it right. NP times delta over NP is delta. I'm going to throw a -1 on there pretty soon. NP here is negative delta squared over 2 NP. True. Go with the delta here. Delta squared plus NP. Forgive me. Yeah, delta squared over NP. I'm sorry. Delta squared over NP. Go with the other one. Negative delta to the third. Negative delta to the third over 2 n squared p squared. Okay, let's keep crossing these bridges, guys. There's more over there. Let's go over here. NQ here, NQ, bring it across. Negative delta, that's pretty telling. NQ times this is negative delta squared 2NQ. Negative delta. Negative delta times this is positive delta NQ. Positive delta squared NQ. This is positive delta cubed over 2 n cubed n squared q squared. Yeah, we said, remember now, these are all negatives in front, guys. Multiply all, this was all negative. That should have been a negative right here. That should have been negative of a negative, which is positive. Everything's got to be the opposite of what you got. What's the opposite of this thing? Opposite of negative is positive. Opposite of negative is positive. Opposite of positive is negative. Opposite of positive is negative. Same thing right here. Opposite of positive, opposite of negative, opposite of positive, opposite of negative. There's a lot of other stuff going on. Ladies and gentlemen, there's negative delta. And there's positive delta. Positive delta and negative delta are out of there. Now it gets a little messy, but now we got to figure out what we're going to say. All right, so let's try to put these together a little bit. Just want to confirm my notes, and I think I got a feeling I was looking at my notes at another time, and I wasn't too comfortable with it on this particular aspect. Everything else is the very major aspects of this whole process, which is what we've done so far with so much of this stuff. We're absolutely comfortable with it. We should be comfortable with it. Sokolnikov and Redheffer and Courant and John and other people, some of the people we had talked about, Turner and some other people, they really knew it. They really knew the stuff. So we're confident. Overwhelming majority of the things that we're talking about, we're absolutely confident about, and the most important aspects of what we're talking about, which is the most important, we're absolutely confident about it. For the most important aspects of what we're talking about, we're absolutely confident about it. So we got up to here. All right, so what? What are you doing? What are we doing? Okay, we'll cross this bridge. So I couldn't just throw out the trivialities because everything was kind of trivial after. I mean, there were trivialities in some places, but they were overwhelmed by other things that were going on that were essentially non-trivial, and they converged to something non-trivial. These right here, they're all relatively small, so we got to work with all of them and see what we can do, and that's kind of why we're going here. I'm not throwing away. We threw away certain things because it was so close in the big picture, because there was a 1 in there, and what did 1 minus something or 1 plus something, the something was so small, it was like 1 times 1, which is the 1 that we got, and that's how we got the A here. You can't do that in all instances because you don't have something to which it's going to converge to really easily. 1 minus 1 over a trillion is awfully close to 1. 1 plus 1 over a trillion is awfully close to 1. If I multiply the binomial 1 plus 1 over a trillion with the binomial 1 minus 1 over a trillion, yeah, it's 1. It's awfully it's close to 1. But you could do that because the circumstances were such that allowed it. Other times you can't. You got to keep it, and then you round off at a different point. And that's kind of the argument here, guys. Trying to make some sense out of this thing, guys. What we could say here, there's a lot of ways to go. Let me just kind of write it down here if I can. Do you think yeah, I got an idea right off the bat. This one right here, put a 2 on the bottom, put a 2 on the top. These guys are already out of here. And relatively speaking, they're pretty big. See, that's why you can't really throw stuff out too easily, guys. None of them are, the D, these other things, we can debate them. We'd have to look at the numbers. I don't want to say too much right now on that, but look at this and look at this. Put a 2 on the bottom, put a 2 on the top, you're here. Good enough. Plus delta to the third over 2n squared pi squared. P squared, rather, I'm sorry. I think you might see where I'm about to go here. Look at this right here, ladies and gentlemen. We've got this right here. This is NQ. This is 1NQ. This is 1NQ. This is 2NQ. Multiply by 2 over 2 on each side. And you got delta squared over 2NQ plus negative 2 delta squared over 2NQ. Oh, this is rather, again now, I don't want to beat this up too badly, guys, but this kind of like easy one to look at, it's easy to look at that it disappears, and it's surprising that it disappeared, I guess. The way things go sometimes, you think it's going to be a little more complicated, but you have negative delta, and positive delta, 0. Negative delta plus positive delta is 0. Get these together, get to here. Get these together, you got that. I think some of the argument is, and I could be jumping the gun. If I am, then I am, and I'll have to correct myself. But we already know that n is huge. N is huge. If you square something huge, it's really huge. Delta ain't that big. Delta we said was, at the end of the day, delta was r minus np. And that wasn't, you say, what are you talking about? It's got to be big. N is big, you just told me. Yeah, I know. But n squared is even bigger. Yeah, that's true too, but yeah, you're getting more than that here. Well, okay, let's time out for a second. R is big and NP is big, and the difference between them isn't really that great. That ain't a big number compared to this. So a lot of it's probably going to fly out the window. Let's just see what happens. Let's throw these guys somewhere else. Or at least close to equal, right? Close to equal. I truncated a lot of stuff to begin with. Let's talk. Here's a negative 2. Here's a negative 2 delta squared. Here's a positive 1 delta squared. Negative 2 delta squared and positive 1 delta squared. Negative 2 delta squared and positive 1 delta squared is negative 1 delta squared over 2mp. Yeah, true. Add these two together, you get negative negative 1 delta squared over 2nq. All right, this is, like I said, we got to be careful. NPQ is a lot bigger than delta. So, man, when you start squaring it, it's really a lot bigger than delta. It's a lot. I mean, it's not necessarily. Let's see here. I think there's like other numbers that come in. We could have taken this a lot further out, and that was kind of my issue with it when I first looked at it. But we're not. That's neither here nor there, I think, for our purposes. Man, I'm really tempted to do something here, but maybe I shouldn't. So let's say this. When I'm looking at it, we are going to say. Yeah, this is the hardest part of the whole thing, guys, and it ain't much. Let me see here. For some reason, right. I had written a 3. I had written a 3 right here rather than a 2. If Dr. Sokolnikov, I don't have his book in front, I'm sure he did it right, and I am absolutely sure that I did it wrong. I shouldn't have written a 3 here. I should not have written a 3 here. I should not have written a 3 here. Should have been a 2. Should have been a 2. What I have here is fine. What I have here is fine. I wrote a 3. There may have been other as you consider this multiplication, perhaps you can argue that a 3 does arrive there. I'm not prepared to say that's not the case. I would tend to doubt it, though. I think I just flat out made a mistake. But here's the big takeaway. Here's the big takeaway. You saw me do it. You got it on film. This is the right way. This thing right here, R minus NP. The argument that they're making, regardless of the 3 that I wrote there, maybe there's more iterations. If you did more iterations in the multiplication, perhaps you would arrive at a 3 there. I doubt it. I doubt it. I think I just flat out made a mistake. Doesn't matter. Whether that's a 3 or a 2, we threw it out. I guess if there's ever a time for an arithmetic error, it'd be right there. Because in either case, that term is trivial. For large values of n, for large values of n, this thing goes to 0. Whereas in this case, it's not. The argument that Sokolnikov and Redheffer make, and other people make, obviously do this. You can throw this out because it goes to 0. You cannot throw this out. That's why we weren't really playing the game with 1 plus delta over NP and 1 minus delta over NQ. Yeah, there we got away with it. But you saw me do it. We got away with it. It worked. That was fine. They go towards 0. So does this. So does this. So does this right here, guys. But the other ones don't. And that's important. You're probably wondering, yeah, so what? Good luck, It's not as bad as you think. Can you try to be a little more efficient here, guys? Okay, so just watch out for that in my notes. There's a 3 where there likely should have been a 2. In fact, not even likely. It's very, very likely to the point where it should have been a 2. There's a 3 in my notes right here and right here where it should have been a 2, but it doesn't matter. If ever there's a good time to make a mistake, and there's really never a good time to make a mistake, these guys go to 0. These guys, in the limit, these guys are going to 0. Regardless, they're going to 0. So we lucked out. These do not, though. These are the ones that we're going to count. Can I talk to you? Can I put a Q on the top and the bottom? So this one already had the Q. Can I put a P on the top and the bottom? Okay, everybody understand that? Watch carefully. Let's write it again because it's very important. Negative delta squared over 2np over 2np and negative delta squared over 2nq. And I want to give myself a little more room, that's all. That's a -1, that's a -1. No big deal. All right. Got more to ask. Can you multiply by a special one called Q over Q? Can you multiply by a special one called P over P? Aha, we got a common denominator. We will add the tops. The tops are negative 1 delta squared Q plus negative 1 delta squared P, which is the same as P plus Q right here. Is that true? Negative 1 delta squared P, negative 1 delta squared P, that's that. Negative 1 delta squared P, that's that. Negative 1 delta squared Q, that's that. The bottom is 2PQ. Again, it's a bold move. I mean, we threw everybody out. Except for a few items. We took 4 items, we combined them, and we got to here, and then we said, no matter what's going on beyond those 4, if n is really, really big, in the limit they go to 0. In the limit, they go to 0. They're not important. There's an infinite amount of terms, ladies and gentlemen, that we're adding together. There's an infinite amount of terms that we're going to end up adding together. Yeah, I agree. You are. We are, conceivably. We're saying that after a certain point, there just isn't much there. Perhaps they're doing it with the multiplication itself, when they're doing Taylor's formula for each scenario, with the 1 plus delta over NP, and the other one being the 1 plus a negative delta over NQ. And they're not throwing it out, they're keeping it, they're doing it, they're getting the Taylor expansion for each of those circumstances related to the function ln of x. For both circumstances, they're doing it, and then they're saying somewhere in that array, I'm only going to worry about a few terms in each expansion, and then I'm going to combine. And their argument is everything else is trivial, and the bigger that n gets, the more trivial that everything becomes, and only those few things that you add together are going to matter, and then we're here. True. Yeah, true. I mean, according to them, it's true. It's believable based on what they said. It's not. I don't want to say that it's very, very outright intuitive, but it's believable enough given what they've told us about the size of NP, of NPQ. The size of NPQ, how does that compare? If NPQ is really big, MP is really big. NP is even bigger. So we're okay with that. We're not. We can believe a lot of this stuff. We know that the probability of one of two things happening in any one trial, one of two things can happen. Success with probability P, or if it's not success, then it has to be the other thing, and that's failure. The sum of the two probabilities is 1. That's great. What does that mean? It means what you're looking at. Yeah, true. Now what we have, there it is, you're looking at it. ln of the binomial expansion times A equals negative delta squared over 2n. Man, and we, See how many times I almost wrote for NP, I wrote mu, almost. NPQ is the variance. Again, all of this follows from the earlier assumptions that the absolute value of delta is tiny. Absolute value of delta is tiny compared to NPQ. If it's tiny compared to NPQ, it's really tiny compared to NP, and really tiny compared to NQ, because both of them are usually bigger, aside from some some special circumstances. All right. Well, I'll tell you what. It's kind of getting us where we want to go, guys. If two things are equal, if you exponentiate each side, they're both equal. You got it to here. Two, NPQ is the variance. That's the standard deviation squared. It's sigma squared. If two things are equal, this item, the natural logarithm of all this, put on top of the base of the natural logarithm, e exponentiated to this power, the inverse of the logarithmic function, yeah, that's true. Yeah. I'm gonna write it somewhere. I just think you guys see a little bit better over here. Write it down anyway, but then we'll take it from there. This is 1 over a, divide by a on each side, e to the negative delta squared over 2n pq. Okay, what's A? Yeah, we already said what A was, in a sense. I mean, we got this right here. So a lot of stuff. Let me... Okay, guys, I mean, we've got this. We can always reverse it, look at it. It's always debatable where you're going to, what kind of answers you're getting, but approximations at some point are something that's very, very clear in the sense that they're going to zero and you can just truncate certain things. Let me see what I can say. Yeah, there's a reason they call me the chalk man, okay? Let's see what we got. Remember we said divide by A on each side. The binomial probability for our successes, divide by A on each side. Yeah, A is equal to this, ladies and gentlemen. 2 pi n p q e to the negative delta squared over 2n p q. Yes, true. We also said that the variance, we've been giving heads up on this all discussion long, I guess. N squared is NPQ. Forgive me. Sigma squared. Sigma squared is NPQ. Sigma is the square root of sigma squared. Sigma squared is NPQ. Sigma is the square root of sigma squared, which is the square root of the product, NPQ. This is the standard deviation. This is the standard deviation. This is the variance. We've been there. We have definitely done this. That puts us in a neat spot. It is at least approximately equal to this, according to the arguments we've been making. What does that mean? The binomial, the probability of this binomial distribution, of the probability of our successes, when R is a big number and N is a very big number. N is very, very big. The probability of our successes is approximately equal to. What do we got? Well, you got this thing right here, this is the square root of 2 pi. You basically got that right there, square root of 2 pi n p q is square root of 2 pi times the square root of npq. Square root of 2 pi, the square root of 2 pi times the square root of NPQ. This right here is sigma. That's the square root of 2 pi. This is delta squared. N pi q. Yeah, that's sigma squared. NPQ, that's sigma squared. What's it equal to? Equal to what you're looking at. I mean, it's square root of that is sigma Yeah, true. That's the square root of NPQ squared. Well, the square root of NPQ is sigma. When you square it, you get NPQ. Sigma squared is NPQ. It's the variance. Yeah, I mean, it's easy. Like you've heard me say many times already, ladies and gentlemen. You've heard me say this many times. It's easier done than said. I mean, saying this stuff is a little more, it'll win you a little bit more than actually doing it. I mean, just doing it's not too bad. But it's still, there's a lot here. There's definitely a lot here. And there it is. That's that. Well, what does that mean? Well, the probability of the number of successes being between R1 and R2 is going to be something like this. I'll show you. So we did... Take this right here. Yeah, that's true. So what do you want to say here? Well, if you were going to find the probability of the number of successes, let's say this is just the probability of the number of successes being R. What if I wanted to find the probability of all the successes between R1 and R2? I guess I'd have to add up all of these on the right-hand side. This is the probability of success. This is the probability of R number of successes. Right here. This right here is the probability of R number of successes. This is the probability. The probability of R number of successes is this right here. True. You got to remember now, sigma does change. You got this. It's a lot here. Let me just kind of think here. No, delta is, yeah, there it is. There it is. Delta is R minus NP. This ain't changing. This right here is going to change. The delta is going to change. What does that mean? Well, you know, you're going to have to vary it. Let's say it's a set number. There's zero success. There's zero. R is equal to zero. Zero number of successes. R equals one success. R equals two successes. R equals three successes. R equals four successes. You get it. Out of 1,000 times, I'd like to know what's the probability of there being zero successes, or one success, or two successes, or three successes. I want the range from R1 to R2. Well, then I'd have to find out what one of these is. Then I'd have to find out, using this, where delta is equal to this, where delta equals this, and, you know, where delta equals that. And, yeah, I mean, R minus NP, see what you got. So let me just see here, guy. I want to always look at the beginning of what I'm doing. Right. You know, delta is R minus NP. R minus NP. Okay, so, and we're saying it ain't really a big thing, but I got to account for it, and I'm going to have to do that. Hey, man, I want to go from what are the probability of 5 successes all the way to 20 successes? R is 20. R is 5. Put it in here. This doesn't change. Assuming you know for that many trials, that doesn't change. This does, potentially. R equals 5. Plug it in there. R equals 5. Oh, well, there it is. Now, find for R equals 6. Plug it in here, minus NP, the whole thing. R equals 6. Oh, yeah, put that D in here. Get it. That's for B6. Then you'd have to add that. So this R would be B5. After it's 5. B5, B6, B5, B6, B7, B8. It's got to be a discrete number, let's say. for now. B5, r equals 5, r equals 6, r equals 7, all the way to 20. What does that mean? Add up B evaluated at 5, B evaluated at 6, B evaluated at 7, B evaluated at 8, dot, dot, dot. B evaluated at 20. And that's, though everything stays the same, ladies and gentlemen, except for this. Except for delta. That's going to depend here. You're going to put a 5 in here, and that stays the same. This might be, the answer here might be 30, you know, and then say 30, you know, or whatever it is. And. Okay? See this r minus np, this r minus np is not really a big number necessarily compared to np. And that's why we were able to throw out certain things to get this value. And they talk, and I talk about it. You know, I mean, I say, and obviously Dr. Sokolnikov talks about it brilliantly. Yeah, you're basically, I mean, you're summing from r equals r1 to r2, let's say it's discrete and it's just regular numbers. This will give you the probability, and I have it in the notes, guys, probability of the number of successes being between r1 and r2. And my friends, that is summation from r equals r1 to r2 here of 1 over the square root of 2 pi times sigma times negative delta squared You've all got it. I mean, we're looking at it. Okay? That's the key to the whole thing. There's some stuff that goes on. You know, how are you going to do it? And they say some stuff here, guys. Let me see what I can say here. It's going to make a little bit of sense. We've made it make a lot of sense here. They do some other stuff. Let me just so that's interesting. Well, there's a summation going on there, guys. There's got to be, I don't know, for lack of a better word, there's got to be a pattern here. And a pattern that maybe we can, a pattern that we can exploit for the purposes of making this a continuous distribution and finding out what happens with a continuous variable, with continuous quantities. I mean, that's so often how things happen in nature anyways. You want to look at things from a continuous standpoint. There's something discrete here, obviously. You're going by ones. Who says we got to go by ones? We can go by infinitesimal increases or infinitesimal decreases. Can make it a straight out calculus problem beyond that. There's a lot of ways this works, I guess you could kind of say here. They're saying, telling us to remember, I guess. I almost drew that correctly. There's just about no way to draw this correctly as far as I'm concerned. But anyway, there's the approximately equals, and it's pretty darn close. To R2. Okay, we've done the discussion on this. Okay, we got this. For successive values, so basically we're kind of remembering, guys. We've been there, we've talked about it. Let's get a delta. The delta, the change in the delta values is actually 1. Because for successive values of delta arising from successive values of r, the r is the only thing changing here. The NP doesn't change. So that's how you're getting this for successive values. If you got r equals 5, I don't care if that's a billion right there. 5 minus a billion, whatever. Now put a 6 here. 6 minus a billion. When you subtract the two, 6 minus 5 is going to be 1. The billion don't matter because it's occurring twice. That's what they're trying to say there. Then they say, okay, man, let's see if you can do something here. Because maybe we can kind of play a game here and see what's going to happen. Let me see how strong I want to take this, guys, when we're doing this thing. They said, why don't you take t? Dr. Sokolnikov and Redheffer tell us, why don't you take t and define it by delta divided by sigma? Well, wait a minute. Sigma, for a given experiment that doesn't change, and for a given number or experiment or process, whatever, for an identical process that's not going to change, and for n not changing, sigma squared is npq. Sigma is the square root of npq. It don't matter. If n doesn't change and p and q don't change, sigma squared doesn't change and sigma doesn't change. It's about as simple as that. Sigma is the square root of the product npq. That ain't changing. Delta changes. How does it change? Well, I already said it changes. It's changing by ones. All right, sounds good to me. So what does that mean? How would delta t change? Delta t, the difference between r plus 1 and r plus 1 minus r is 1. So this guy would be something. The one subsequent to it would be 1 more than that. So 1 more than that minus that is just 1. The sigma stays on the bottom. So at the end of the day, what you get is delta delta over sigma, the way Dr. Sokolnikov says it, and that's 1 over sigma. I already sort of said that. Following Dr. Sokolnikov, in his brilliant, and Dr. Redheffer's. I'm assuming it was Dr. Redheffer as well. So you're looking at this. Delta t is 1 over sigma. We will expand this shortly to a continuous distribution. What's going on here? Well, they told us to remember this. going on here? Well, okay, let me just check the audio on this, guys. I think we're good. Okay. Pretty important stuff here. Just some beautiful, Dr. Sokolnikov and Dr. Redheffer, I mean, their mathematics is beautiful, and we're fortunate to have it because look at the stuff that we're learning from great scholars like these people who did some great work, tremendous work. We'll expand upon this shortly to a continuous distribution. We said this, I wrote that. What the heck? I mean, the way that we can kind of do it is, this is simply the way it is. Now, delta itself is gradations of 1, we said. We kind of saw, delta is 1. Then the argument that Dr. Sokolnikov and others give us is why don't we just do this again? Okay, we already said this. We're not going to debate this. T is delta over sigma. T is delta over sigma, and so what is that? So what? What's the big deal? Well, T is delta over sigma. We said that over here, and we said that R was discrete in the sense that it's R equals 0, R equals 1, R equals 2, R equals 50 billion, and R can equal 50 billion plus 1, and it can equal 50 billion plus 2, 50 billion plus 10, you name it. But it's discrete, it's 1. How many successes are there? Okay, that's the big thing. True. What if R didn't change like this? Yeah, I know, R goes from 0 to 1 to 2. This guy is stuck for a given number of iterations, for a given number of trials that this is being done. I get it. But what about him? Well, R can be 0, can be 1, can be 2, can be 3, can be 4. We got a pattern here. It's delta, delta. Delta small delta is 1. Yeah, but it doesn't have to be from 5 to 6. It can be 5 to 5.1 to 5.2 to 5.3 to 5.4 to 5. Heck, it can be even more. It can be even more continuous. It can be 5 to 5.001. After that, 5.002. After that, 5.000, whatever. I don't know how many zeros I put in there. 5.000, 3 zeros. 5.001, 5.002, 5.003. And you can really expand that if you want. The trick here is sigma is a constant. We're going to say that ladies and gentlemen, if the numbers are big enough, my friends, if the numbers are big enough, sigma is what it is for a given n. NPQ is what it is, and it just stays. NPQ is a constant. How does it change here? If this was continuous, it'd be d delta equals 1 over sigma. dt d delta is 1 over sigma. dt d delta equals 1 over sigma. dt equals 1 over sigma d delta. you wanted to say that. T equals delta over sigma. You could say a lot of stuff. I mean, if you really wanted to, I don't know how much I want to beat this thing up, guys, but what did we say? We said define T as delta over sigma. That means delta, by definition, is sigma times T. d delta dt equals sigma. d delta equals sigma dt. I mean, it's not that hard to look at, but I guess you could kind of say, you know, how you want to play this thing. I mean, how do you want to define this thing? The gradations are 1 over delta. You know what I mean? So how would you get that? You know, I mean, the delta t for change in t would be another sigma. There's 1 delta t, there's a change in 1. 2 delta t's, there's a change in 2. That would make sense. If delta t is 1 over sigma, dt d delta is this. You know, yeah, dt is 1 over sigma. Delta t is 1 over sigma. dt is 1 over sigma times delta t times delta times d delta. If it's by 1, then it's changing by 1 every time. Just want to kind of see here how you want to define that. Yeah, I mean, this can get kind of crazy how they're trying to play a game here with this stuff, guys. I guess what they're trying to say is the deltas are always like this, but if the delta was, so however much the change in delta would be, dt d delta would give you 1 over sigma, and that's true. And if it's every time it's by 1, it's 1 over sigma. But if it's less than that, it's indeed something different. So if the d delta is not 1, but it could be just something discrete, then it's 1 over sigma times d delta. So that's kind of where they're coming from on that. And that's where we're getting right here, guys. That's where we're getting right here. All right, let's see where they want to go with that, if they're going to play that. And you could play it, like I said, you could play this a whole bunch of ways, guys. However much sigma was, I mean, it's really kind of a touchy matter here. How you want to view it. I mean, some value of t times sigma. Yeah, and t would have to be 1 over sigma. So yeah, I mean, there's a lot here. They play a lot of games, guys. But and here's 2 of those games I guess you could play. You got this, which may be of use, and you've got this. Look, it's a horse apiece. It just depends what you want to solve for. If I want to solve for d delta equals sigma dt. If I want to solve for dt equals 1 over sigma d delta. They're both born from the same thing. So if that's the case, let's see how I'm going to do this, guys. Well, it's all here, guys. It's pretty tough. We're almost there. Hang in there with me. All right, I mean, we've said some stuff. We did the summations between particular places that we're going to go. Like I said, the way we looked at it, we said T was delta over sigma. I'm in the back of our mind here, guys. Over sigma, and if you're gonna play that game, there's a whole bunch here. Let me just make sure I'm on the same place, same location they are. Let me go. They're solving in terms of dt, so let me stay there. If t is this, dt is one. Delta t is 1 over sigma. Yeah, true, but yeah. But not if you're going to make this continuous. It's going to be, dt is going to be 1 over sigma, but this can vary. Small, big, very, very small is what we're kind of looking at. So we're looking at 1 over sigma, delta, delta. And that is huge. And that's probably where we should have stayed in the beginning. I kind of gave you a bunch of looks at it, but there it is. Okay. So if you want to stay here and you want to play the game right there, guys, let's do it. Okay, so let's talk. I mean, the way it was going is, and I'll throw these things in here like I can. Let me not put the limits right now, guys. Let's just kind of write what we worked hard to find, and that is this. Sigma is the square root of NPQ. This is E, negative delta squared over 2 NPQ, which is this. All right. Yeah. True story. Add them up. Yeah, definitely a true story. And you sum them. And when you go d delta, remember what we had said, delta, we said a lot of stuff is what we said. I mean, we looked at d delta, you guys, and we looked at it and we said delta t was 1 over sigma, d delta was whatever it was. Again, we said that t, again, I hate to keep emphasizing this, guys, but it's a pretty important point. That ain't changing. That is, if it changes by ones, then subsequent terms are always looking like this. Yeah, it's a true story. It is. If you're gonna go, that's what the d, times, that times the d delta. You could even say, the d delta, the delta delta is 1. So you're talking basically this. Delta delta is this. Yeah, true. But they're kind of looking at it and saying, okay, yeah, that can I guess make sense. How does it change otherwise? Well, if you go dt d delta, yeah, it's just by 1. It's 1 over sigma again. Yeah, but the d delta is not 1 now. It's something less than that. So this kind of sets in motion that the delta t is 1. Yeah, we all get it, you know. Or the delta t is 1 over sigma. But here the delta t is much more different because the delta delta is 1, but the delta delta can get as small as you want it to be, and then dt can get as small as you want it to be. So that's huge. That's huge. So you stay right here. And that's here, if d delta is 1, that doesn't change. Look at, I'm blocking it out. Look everything to the left of, look right in front of me. Forward here, all this, all this. If this is 1, that's how it sums up. But what if d delta is not 1? Remember, guys, I mean, delta was r minus np. You know, I don't think that's legible to save my life, but okay, you know, you get what I'm saying though, guys. I mean, delta was r minus np, and the way that it was changing, delta delta was by 1s. You know, delta delta was by 1s. So that wasn't a big deal. I didn't need to put it there. Yeah, I know, because it's going from r equals 10 to r equals 11 to r equals 12 to r equals 13. I get it. Yeah, I know, because r is 0, 1, 2, 3, 4. I get all that. What if it's not? What if it's 0.1, 0.2, 0.3, 0.4, all the way to 0.9, all the way to 1.0, 1.1, 1.2, and then goes all the way up? If that's the case, then delta delta is 1. Delta delta is 0.1. And you're getting a little more accurate. And if you make it completely continuous and keep summing this thing, it's going to be an integral. If you make it completely continuous, it's going to be an integral. And so you go here, and didn't we say that delta's that, and it could, you know, delta delta is what it is, and you know, I keep going to that t. I like the t here, guys, but let's, you know, you can view it a bunch of ways if you want, but if you want to solve the other way, delta delta is multiplied by sigma on each side. Sigma dt. I mean, they defined it. It was kind of a weird definition to begin with. What's, you know, where are you getting this from? Where am I getting it from? They just made it up. T equals delta over sigma. T equals delta over sigma, and we know that delta, that t is in discrete intervals. Well, I don't know if you can say that. I mean, it's not really a discrete interval. There's a lot going on, but it does have certain intervals. When you go dt, d delta, it's 1 over sigma. True. To delta, you guys, and okay, fine, that's what it is. How do you want to change this thing? Well, if delta's like this, how delta change, and sigma's a constant. T and delta are really close to each other. This is just 1 over sigma times delta. If you want, T and delta are very close to each other, in a sense. They're off by a factor every time you consider them 1 over sigma. And 1 over sigma is a constant for a given situation. That's delta. So T is got an attribute associated with it. And when you get differences of it, How different are they? Just by 1 over sigma. Yeah, 1 over sigma if it's discrete. What if it's not discrete, though? You know, what if it's not discrete? So you could say whatever that is times sigma then it's this dt yeah, they're off by a factor like that. Delta delta is sigma delta t. It's kind of the big picture, guys, in this whole thing. Well, if you're going to do that, and let's really keep making let's make delta really, really small. If you're going to make delta really, really small, you're going to make t really, really small, and we're talking about it's not discrete anymore, guys. D delta is sigma dt. And delta, yeah, I know delta's this, but is delta written another way too? Yeah, up here. Delta equals sigma t. That's why d delta dt is equal to sigma. D delta dt is equal to sigma. D delta is equal to sigma dt. True. Delta is sigma dt. Is sigma t rather. So let me see here, guys. I'm close to running out of chalk. Let's see here. Not really. I got more. What's going on here? Delta, ladies and gentlemen, is sigma t. Delta is sigma t. Never been good at writing sigma like that, but okay. Delta is sigma t. That is sigma t quantity squared over 2 sigma squared sigma dt. True. What happens is, all right, guys, we beat up the t equals delta over sigma pretty good. As long as we're consistent, we're okay. We got, to visualize this. Again, writing this stuff down is easier than visualizing it. So like I said, some things are easier done than said. Some things are easier said than done. But this is pretty challenging stuff. But I believe pretty worthwhile. Thanks for hanging in there, guys. Let's get almost there. So what do we got? That's equal to, here we go again, 1 over 2 pi sigma e to the negative see what we got, guys, to the negative e to the negative sigma squared t squared over sigma squared. you square this, guys. You know, this is where it is right here, right? You know where it's going. I mean, this is the negative stays. Square of this product is sigma squared t squared. That sigma and that sigma go. You're summing these. Well, heck, if they're small enough, it's called an integral. If the steps you're taking, if they're not delta t anymore either, if the dt steps that you're taking are small enough, we're talking about an integral. So what happens here, you know, there's a lot being said here. So this thing right here, at the end of the day, it's an integral corresponding to the R1, R2, but this time it's go between t's. What does that mean? I guess we'd have to find out a t. I mean, how big is this t? Well, you got to remember, t was equal to delta over sigma. So between two t's, you're looking at a situation of, a particular value. Let's say, you could be taking a value of, where could we do this now? How do we want to do this? You could say x sub 2 minus np on the high end, x sub 1 minus np on the low end. That's delta over sigma. And this is T2, and this is T1. Wait a minute, that's like mu. That's like x1 minus mu over sigma. There's your T1. x2 minus mu over sigma. That's your T2. They're saying something like this. If you're going to do this, well, you saw what I wrote, guys. Well, heck, if you take this thing far enough, if you make dt very, 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 very small, if you make delta t very, very, very small, and it's a dt, and the dt is really small, you're talking about an integral and you're done at the end of the day. So let me see here. You got this. You got this. You put, if the 1 over the square root of 2 pi is a constant, and you know it is. And that's this. In the limit. It's the Laplace de Moivre limit theorem. Yeah, that right there, whatever it's going to be. Well, you know, I can get all kinds of approximations. As n goes to infinity, my friends. As n goes to infinity, the probability of this inequality approaches this limit. You know, I'm saying, we just saw what I said. There's an x associated with it, there's an x associated with T1, period. That right there is a fancy way of just saying sigma. Or maybe this is an easier way of saying sigma. We can debate that one. That's sigma. That's what I talked about over here, my friends. I'm sorry. And then this is T2. The probability of this, you know, I don't know how the symbolism, you know, probability of this, you know, they didn't go into that too much, so I'm not going to. Probability of this above wow, it's an incredible conclusion. It's not only an incredible conclusion, but we better hope it's right. And everything seems okay. Everything's fine, consistent with all the mathematics that we've talked about. There's nothing wrong with our mathematics. We used Taylor's formula correctly. We derived earlier that mu is NP, that sigma squared, the variance, is NPQ, that the standard deviation is the square root of sigma squared. It's sigma, and it's the square root of the variance being NPQ. The square root of the variance is square root of NPQ. That's sigma. Square root of the product, NPQ. We used Taylor's formula correctly. We decided when to truncate the multiplications we were doing. We did that correctly. We followed that. At least we jettisoned the terms that were appropriate to be jettisoned. We got rid of them. We made everything okay. We know Wallace's formula. We know Stirling's formula. We used all of this correctly at different points, both in this derivation and elsewhere, let's say. We're fine. We're doing great. We got this right here, you guys. There's just one thing that we hope we answer in the affirmative. We hope there's something here, and we hope that we answer it in the affirmative, and that's this. Since now we're not talking about discrete things like 0, 1, 2, 0, 1, 2, 3, 4, etc. Everything's continuous now. There's an infinite number of possibilities, from negative infinity to positive infinity. Everybody understands NP is a number. Positive number. NP is a positive number. Yeah. So is X. So is X. But if he's less positive than NP, it's a negative answer. If this is 5, if this is 5, if X is 5 and NP is 1 billion, 5 minus 1 billion is negative 990,999,995. negative 999,999,995. Negative. Really? So I can go from negative infinity to positive infinity. Yeah, I know. If you do that, it's certain something's going to happen. From negative infinity to positive infinity, it's certainty. We better confirm its certainty. The integral from t1 equals negative infinity to t2 equals positive infinity, that integral has to be something we can normalize. In other words, how big is it? Well, I don't know. I guess this whole thing would have to be as big. Here we go, square root of 2 pi again. This thing right here, before you worry about 1 over the square root of 2 pi, this thing right here would have to be equal to the entire thing from negative infinity, integrated from negative infinity to positive infinity of the quantity e to the negative t squared over 2 dt, integrated from negative infinity to positive infinity, would have to be the square root of 2 pi. Because the square root of 2 pi times 1 over 2 pi is 1. The function would be normalized. You'd certainly get the answer of 1, because somewhere from t equals negative infinity to t equals positive infinity, somewhere something is going to happen for sure. And the integral from negative infinity to positive infinity confirms that. We got to make this whole thing right here equal to 1. You're hoping that this guy right here is 1. For all of this to be equal to 1, this right here, just right here on the right side, this right here, the integral from negative infinity to positive infinity of e to the negative t squared over 2 dt, that's got to be equal to the square root of 2 pi. Because the square root of 2 pi times 1 over 2 pi is 1. That's normalized. Then we confirm everything. Then everything else is right. That's the one thing that we're worried about. Can it happen? Will it happen? Turns out it will. Turns out it will. And they're different with areas and stuff as well. There's more than I said here, guy. That probability of it happening, they put it at some value minus some other value. And this is for T1, and this is for T2. And I don't want to delve too much into that. It's just the difference between those two. The area under the curve is going to give you that probability. And that's where they're going with this right here. And that's where they got that. That's not as big a deal as right there. I mean, it is a big deal too, obviously. But for the above to be true, this function, as it is, it has to be as it is. We've derived this thing from correctly employing Stirling's formula to correctly employing Taylor's formula to making the right guesses on the approximations, regardless of whether or not we blew some of the addition or something. We just know that some things can be ignored at the very end. And we threw out certain terms. We did it appropriately, and we got everything right. Let's confirm. Is the integral spanning all possibilities certainty, which means 1? If this is integrated from negative infinity to positive infinity, if you're doing the integral from negative infinity to positive infinity of e to the negative t squared over 2 dt times 1 over the square root of 2 pi, that equals 1. It is certain that there is a value of t. There is a value of t somewhere from negative infinity to positive infinity. That is all the possible t values associated with events happening. From t equals negative infinity to t equals positive infinity, from t equals negative infinity to t equals positive infinity, that integral from t equals negative infinity to t equals positive infinity of e to the negative t squared over 2 dt, the result of that integral times 1 over the square root of 2 pi has got to be 1. Turns out it is. We're going to do it. So that's it. That's as simple as that. We're trying to show that, and that's equivalent to show. Okay, so let me walk you through it really quickly, guys. This stuff does take a while. Like I said, it always does, it seems. But I think it's worthwhile for us. So we're looking here And we're saying, okay, it's certain something's going to happen in all the possible, some event of all possible events will indeed happen. What's the probability of that? Well, that's the sum of everything underneath there, man. That's going to be for certain. That's definitely for certain. That's 1. Yeah, I'm hoping it's 1 is what I'm hoping. If I multiply by the square root of 2 pi on each side, the square root of 2 pi is equal to the, I'm hoping that it's equal, I'm about to confirm it. Absolutely. Because when you divide it by 1 over the square root, if it's equal to 1, look, if this thing's equal to the square, if this integral is equal to the square root of the product, 2 pi, then 1 over the square root of the product, 2 pi times 2 pi is 1. So yeah, that's the confirmation. For this to happen, we got to have this happen. Well, that'll happen if that whole thing's equal to that. So, let's indeed show that, and I go into it a little bit. Dr. Sokolnikov goes into it. Basically, they do something really interesting here, and let's just do it. Let me run through it, and let me get us through this, guys. We got this right here. We got this. We can always go back. Let's see here. Here goes. You know what we're shooting for, square root of 2 pi. Here it goes. You say the integral is equal to I. The integral from negative infinity to positive infinity, e to the negative 2 squared over 2 dt. Guys, change the variables up a little bit. That's to say, just put an x there. You'll see where I'm trying to go with this, or where they try to go, where they brilliantly teach us this. I've seen different ways of doing this. To me, this is really the most straightforward. Instead of t, call it an x. That's not a big deal as long as everything else behaves in the exact same manner that it's supposed to behave. Tell you what I'm going to do. Why don't you put another one in there too? This time, don't call it an x, call it a y, the variable. You're going to see why we do this. This is e to the negative y. It's the same integral. That's why they called it that. They just call it dy. All right, well, if you multiply I and I, you're multiplying the integral from negative infinity to positive infinity, e to the negative x squared over 2 dx. The integral from negative infinity to positive infinity of e to the negative y squared over 2. dy. True. Yeah. In the right circumstances, and like I said, I think in the right circumstances, the right kind of functions, the product of two integrals is the integral of the product when done correctly. That's not always going to be the case. But there are a very large class of functions, among which, what I have here, where the product, done the right way, the product of two integrals is equal to the integral of the product. So this is the product of two integrals gives you I squared. The product of two integrals is the integral of the product. And it becomes give myself a little more room, guys. Okay. That's crazy. It is provable. Looking at it, you'd have to really think it out based on the calculus background that you have. You think it out. It takes a while. Perhaps it won't take too long. I mean, it took me a good long time to look at it to see that that's actually true, and you get an intuitive feel for it. For me, it took a very long time. I mean, for other people, it certainly probably would not take a very long time to look at it. But this works. We know that it works. Yeah, well, if it works, let's keep going. Well, we said I squared is the integral, negative infinity. Put them together, guys. X squared plus y squared, that looks like the equation of a circle. Yeah, it sure does. That's huge. Now, if you're in two-dimensional space, you're in two-dimensional space on the xy plane. On the xy plane, origin x equals 0, y equals 0. Z equals 0 too, I guess, right? But at x equals 0, y equals 0, on a two-dimensional plane, on the two-dimensional xy plane, x squared plus y squared is a circle for a given radius. And the radius keeps getting bigger as you move outward. But for a given radius, it is a circle. For a given radius, that right here, I tell you what, I can talk about the points on a circle, where R is the radius associated with a circle. Why don't I just symmetrically go outward with cylinders? Use the cylinder method, and to get the volume of that three-dimensional figure. Remember, everything's in the xy plane for the origin. Everything's in the xy plane as far as like a domain is concerned. The xy plane is the domain, and it maps into the z. It maps into three-dimensional space associated with the z-axis. But the xy plane is associated with the domain. Notice you're doing the integral dx dy, and you're just going to work your way out. There's a circle here. Let's say this is the xy plane. Circle here, circle here, circle here. Well, let me see how big this, right here maybe it comes out a lot. Over here it doesn't come out as much. And then out here, it really doesn't come out too much at all. But why don't you get a cylinder and then find the Find the volume of the shell. Find the volume of part of the cylinder. Then find the volume, find the volume of this cylinder. Find the volume of this cylinder, et cetera, but get a good integral to get that done. That's the premise of the whole thing. And I got that in the notes. It's probably a little more straightforward for you when you do something like that. But the way you want to look at it is, and here it is. Let's do it. So there you go. Usually, and as I said, the notes probably go a little bit slower for you. When you just read it out, it tends to be the case. A lot of people, myself included, would prefer the written note rather than a 4-hour movie is what we're kind of into right now, or even a little longer than that. It probably can go a lot faster for you. But to discuss this, I don't know, hopefully there's some merit to it for you, and you can always go ahead and look at various parts if you want to make some sense out of this thing. But I said, the notes guys, like I said, what a professional I regard very highly. Their professional opinion had said that to me as well. They tend to think that, the written notes tend to go a little bit, maybe a lot faster, but a little bit faster for sure sometimes, maybe a little more clear. Well, guys, if that's the case, you're eventually going to bring it to this, and let me kind of bring us close to the end here on this thing. I squared is the integral, still a double integral, but it ain't going to be you can do a cylindrical. Now, there's different ways this can get done, guys. As r varies from zero, radius could be 0 or it could go to infinity, and the other one goes 0 to 2 pi. I'm not a great fan of this way of approaching it, but it's coming out something like this. I'll show you the way I thought was a little more straightforward. R d theta dr, and that's some of the things we talked about. Again, working kind of like with slices of it all over the place as we change. Well, if you knock this thing out, if you play the whole thing out, there's just a number of different ways this thing can play. But you say integral from 0 to 2 pi. Kind of write it like this, reverse it a little bit, and go for it. I'm not a great fan of this one, but it does work. Absolutely, it works. I mean, very well, in fact. Doesn't Again, we're hoping this whole thing right here, right? It's gonna be the square root of 2 pi. Okay, knock this thing out. Evaluate the integral here. Well, this guy's r. This is the u, let's say. Or let's call the whole thing u. Let's call negative r squared over 2. Let's just call r squared over 2. Let's call that the u. Du dr is 2r over 2. That's just r. That's this guy. R dr. Du dr is r. Du is r dr. So what happens is, this is the integral of negative u du. The r value goes from 0, so the u was r squared over 2, still going to infinity. I mean, it's a little odd how it's going to infinity, but it's going to infinity. This is at r equals 0, that's 0, and it goes to infinity as well, so that's going to work. And then after that, go, the integral from 0 to 2 pi d theta. There's a bunch of ways to do this, guys, but I mean, at the end of the day, if you do this integral, this guy right here is going to be negative negative e to the negative e to the negative u, 0 to infinity. At infinity, let's just see here, guys. Let me just make sure we got it straight. Right, we're going to say 2 pi, right? Okay, yeah. At infinity, e to the negative, or close to infinity, or whatever, very big, e to the negative, very big, is very close to 0. If it's not big enough for you, go closer to infinity, and it essentially goes to 0. Minus a negative e to the negative, no, so this is negative 0, minus a negative e to the negative u is just e to the negative u. Put 0 here. E to the negative 0 is e to the 0. That's just 1. That's all 1. Do the integral. Theta equals 2 pi. I'm sorry, just 2 pi. I squared equals 2 pi. Square root it. This isn't bad. This is not a bad way to do it at all. I've never been a great fan. I like the cylindrical method. I feel like to me it's a little more straightforward. But look what you're getting. You're getting the right answer. You're fine. What I like the best is we also could evaluate using cylindrical shells and thus reduce the problem to evaluating a single integral. To me, that's a little more intuitive. But this works great. You saw it. It works fine. As people have shown on the internet and certainly elsewhere. On the internet, people have shown this, and elsewhere they've shown that you can evaluate using cylindrical shells, and that reduces the problem to evaluating a single integral, you guys. If you were to do that, the single integral, I mean, it's just a lot more straightforward. I mean, at least a lot more intuitive. Yeah, we got the answer we wanted for the other one. Let's get it on this one. Tell you what I'm going to do. Let's take the integral from a radius of 0 to a radius of infinity, and let's call the way this thing looks, this e to the negative x squared plus y squared over 2. And like I said, it's getting, there's a number of ways to go here, guys. Number of ways to go. At least 2 ways to go. I think there's more than that. But let's, like I said, this is... Call that an r squared. How's that? Look, man, I'm trying to figure out how this thing looks, and I'm saying it's centered something like this. If I'm looking at a bird's eye view, x-axis, y-axis, z comes out, and then bam, from the middle, probably the biggest one is right there, coming right out this way, coming right out at you. Down here, the further out you go, it ain't that big, so it's going out that way. So let me get how big this thing goes up. I mean, it does go up, and then let me see next to it how big it goes up, and then let me just go across like that, and let me just keep integrating all these shells from a radius r equals 0 to a radius r equals infinity. That is e to the negative the quantity x squared plus y squared. X squared plus y squared is r squared. Yeah, it's this. And what's going on? At any particular value of r, there is, guys, I guess what I'm going to do is I'm going to find the circumference and then multiply by a dr going this way. I'm going to find the circumference, then multiply by dr. And I'm just going to keep doing that. Well, the circumference is 2 pi r. And I'm going to go by dr, and dr goes from 0 to infinity. To me, I tell you guys, I mean, to me, this is probably the most straightforward of all of them. I mean, I like this one. When I look at it, it's going to get me there, I think. Be interesting to see how this plays out. Wait a minute. Let's call u r squared. No, let's call u r squared over 2. If u is equal to r squared over 2, du dr is 2r divided by 2, that's just r. Du is r dr. So what do we got? Well, du is r dr, so what you got here is the integral from 0 to infinity of e to the negative u 2 pi r dr. R dr is du. R dr is du. Pull the 2 pi out of there. It's already looking like what we want it to look like, somewhat. Remember now, all of this is I squared. This is still I squared. Remember, I had x squared plus y squared, the opposite of the quantity x squared plus y squared over 2. That's from the I squared. It's equal to this. It's equal from 0 to infinity. What's du now? Du is r dr. How does that work? Well, yeah, I mean, the u's right here. The u's right here. Yeah, at r equals 0 all the way to r equals infinity, yeah, I won't need to change the limits of integration here. At r equals 0 to r equals infinity, I'm okay. I'm okay. You do the integral. There we go. I squared equals 2 pi times from infinity to 0. This looks awfully familiar. Yeah, it should. We better got to be getting the same answers, guys. At infinity, e to the negative infinity is 0. Minus a negative e to the negative u is positive e to the negative u. Put a 0 in for u, that's e to the 0, that's 1. Minus a negative e to the negative u is positive e to the negative u, which is 1. No, you're seeing it correctly, guys. I squared equals 2 pi. The square root of I squared is I. The square root of 2 pi is the square root of the product, 2 pi. It is normalized as is, ladies and gentlemen. We can leave it as is. You could have, like, right off the bat kind of caught, there's a number of ways you could have played this, really. You could have brought the 2 pi out of there, and there's an R. You could have done a whole bunch. You could have left the 2 in there, and that's, even that's not a big deal. Yeah, it's pretty fast. It'll work in a number of ways, guys. You look at this, if the R's already there, what could this be? This right here, if you kind of look at it and say, well, I already got the R right here to get me out of the woods. What is the derivative of R squared? It's 2R. If you divide by 2, it's just R. Can I pull this thing off? I'm thinking just negative. The answer would be, just get rid of the integral, because here's what the integral is. Get rid of this. The answer to this whole integral would be negative e to the negative r squared over 2, because if you took the derivative of that, it'd be as it is, whatever it is, times r, which would get you here. Fine, and then the 2 pi would be accounted for somewhere else, but it's all here. It's all here, my friends. Okay. It's there, it's what it equals. If you divide by 1, if you divide by the square root of the integral. And again, you saw the answer I got. Here it is, all here. Yeah, it's normalized that way, and that's the very end of that. All right, everyone. Thank you for your time. All the best to you.